Hello. I welcome you all to the second day of the fifth International Conference on Public Infrastructure and its application. And also welcome to the members from the Tech Expo 2024 titled Digital Trust Ecosystem. I welcome you all and we'll start with today's session. So our first session is an invited talk by Mr. Rolf from California, USA. Mr. Rolf is one of the original authors of the passwordless FIDO specification, and they contributed to the W3C web authentication standard. He chairs and vice chairs multiple FIDO Alliance technical working groups, including FIDO2, Metadata Service, and UAF. Additionally, he has advised government bodies and frequently speaks at industry events on topics such as FIDO, identity, IT security, and blockchain. The title of the talk is Introduction to FIDO Authentication, the Evaluation of FIDO and the Future of Digital Identity. Mr. Rolf, are you there?
Yes, yeah. Can you hear me?
Yeah, we can hear you.
Very good. So good morning, everyone. I'm honored to speak at this conference. As you heard, my name is Rolf Lindemann, VP of Products at Knock Knock Labs, which is one of the co-founders of the FIDO Alliance. And maybe some history, 12 years ago, that was even before the FIDO Alliance was founded, I was given the opportunity to join Knock Knock to work on a bold idea that was intended to change the way authentication works. And that idea then became the first FIDO specification. It evolved over the years, and through my work at Knock Knock, I had the privilege to help many companies deploying FIDO authentication on a global scale. And today, I really would like to share some insights about the evolution of FIDO, some recent improvements we have done, and even an outlook into the future, what things we will likely do and focus on very soon. So let's start with an overview, one of the drivers we have seen in the past. And by the way, this is a slide I've shown in 2014, right, where I was impressed that criminals have stolen 1.2 billion passwords, a very large number. Now, in a very recent presentation, I looked up that number again and found that by this time, meaning roughly 10 years later, it's nearly 10 billion passwords, meaning the problem of credentials being stolen from server did not go away. And there are other attacks like that. We have seen many of those, including the ability to attack two-factor systems, stealing digital fingerprints, also on the biometric side. And the question is, what do we learn from that? Is there something which is always a new surprise, or is there some structure in that? And really, if you look into those attacks, you see roughly there are two types of attacks. The first one that's inside the green frame here, those are the scalable attacks. Those are the attacks that really can address and target many different victims at the same time and with roughly the same cost, where the attacks on the right-hand side are more physical attacks. They are not scalable to that degree because it costs real money and real effort to run those attacks. In the end, we learn things are never 100% secure, so we need to focus on what we call robust security, focus on the scalable attacks first, and that's what we did with FIDO. Quick recap, whenever people authenticate to a remote system, like you see in this diagram, we realize that people have local reach only, meaning if we talk to a server, right, the server is far away, we need some kind of helper device. In FIDO, we call that helper device authenticator, which includes all the security relevant aspects of the authentication. For example, it includes key pairs, private keys dedicated to one app. So not only one key pair, but essentially one key pair per relying party or per user account that you have. That also means that the server on the right-hand side only needed to store a public key, and remembering the millions and billions of passwords that have been stolen, with only public keys on the server, there's nothing to be stolen, no credentials really, so we can already protect against this type of attack there. The second part here is the user verification, right? You want some user involvement to verify whether the right user is approving the transaction or trying to trigger the authentication, or at least whether there is some human being, some user that can give you a presence check as opposed to just malware sitting on that device. So that is what we conceptualize talking about and call user verification versus user presence. So whenever the authenticator is about to exercise a key, that user verification needs to be done. The user verification itself is also part of that authenticator. It's a task of that authenticator. Now, what we do for the remote communication, right? This is a local interaction with the user verification, which is biometrics, which only work locally. Now, remotely, there's a cryptographic challenge response protocol we run where we use the keys, we get a fresh challenge, a random challenge from the server, and provides a signed response, which was generated by the authenticator back to that server. We also allow the server to look up the characteristics of that authenticator. So authenticators might have a model ID, the AAGOID, which talks about that authenticator model, what it is, right? Whether it's from one vendor or an authenticator from a different vendor with different characteristics. And the FIDO server can look up the authenticator characteristics from the FIDO metadata server to learn more about that security level the authenticator might have, potential certifications the authenticator might have, and other detailed characteristics. Now, what that means in total, that we get out of that trade-off scenario where you have systems that were either usable or convenient for users or secure on the other hand. And if you depict that in a two-dimensional chart, you see that with passwords, right, you have really poor usability and very weak security. With OTPs, you get a little better security, but the usability really suffers from that. Where the observation is with the concept of FIDO, you improve the security significantly, and at the same time, you also improve the usability for that. So what we really get to that with FIDO, we have an open standard for simpler and stronger authentication at the same time using public key cryptography. And I will talk about more regarding the cryptography versus infrastructure, PKI versus public key cryptography a little later. So it's really there's a single gesture, even for multi-factor authentication, not two different steps. It's possession-based because you need to have the authenticator itself. It's phishing-resistant authentication because those credentials are related to an account and the relying party at the same time. Now, the life cycle of the authenticator typically is you have to register authenticator first, you have to bootstrap the new device if you get a new device, and then re-authenticate, right, subsequently on the same device. And if you look at the traditional way we do that in FIDO, right, for registering the first authenticator, we typically require people to sign in using a non-FIDO method, right, the legacy authentication to understand who that user is that then will register the FIDO credential. For bootstrapping a new device, right, that was using non-FIDO methods to then register the authenticator on that new device, right, or the new authenticator. And if there would be an authenticator available, right, use non-FIDO methods or a security key to be plugged into that device. For re-authentication, this is a simple use case. That is what we addressed, right? Single gesture, multi-factor authentication. So the re-authentication from that perspective is really the use case we addressed with FIDO early on. And we will get and see how FIDO was developed and evolved over time. So it really is benefits for the user. No need to think about devices when using passwords. So that's the difference to FIDO, but having a strong device binding and that provides strong multi-factor authentication when using FIDO. From a historic perspective, you see that the first FIDO specifications were really kind of twofold. We had a passwordless FIDO specification providing phishing-resistant MFA, but only in native apps and only using platform authenticators. Where on the other side, we had security keys providing phishing-resistant MFA in web applications using security keys as a second factor, which typically requires a password as a first factor. So it's really, you see, FIDO was a twofold world, right? Passwordless on one hand side and security keys on the other hand. In the second generation, we then made sure that passwordless would also work with security keys. That's a change number one. And number two, that passwordless would also work with security keys in web browsers. So we brought the security keys to the native apps on one hand side, and we brought the passwordless authentication and the platform authenticators to that to the browser world as well, which were very significant improvements there to get FIDO across all the different application types like native apps and the browser, and allow you to use passwordless in web apps and in native apps as well. Right? So really bring the two worlds together, make it a single world. In the next revision of the specification, or the big milestone was really to be able to use a phone as a security key, which is now called FIDO cross-device authentication. And second, allow the use of biometrics without a PIN in a security key, right? So further step to make security keys and platform authenticators very similar on one dimension, and second, reduce the difference between security keys on one hand side, which were portable, and platform authenticators, which couldn't roam to and be used with other devices, right, through the FIDO cross-device authentication. In 2022, there was another big step forward, and that was on multiple dimensions. The first is we introduced the term passkey and an icon along with that. So the first time we really had a consumer-facing branding, if you will, from FIDO. And if you do a Google lookup and see how many hits you get, right, how many different search results you find, if you look up that term, you see that there's really a big spike, right? When people started talking about a single term as opposed to using your device, right, to authenticate whether it's you. Now you could say, use a passkey to authenticate, and people would understand that, platforms would use that icon as well. At the same time, we added one more thing, and that was the support for synced passkeys, meaning allowing an ability for a FIDO credential to travel from one device to the other, and especially realizing that users typically have multiple devices. right? So I have a smartphone, I have a laptop, and I have a tablet, and it would be very inconvenient to register multiple credentials for each of those devices individually. It's much more convenient for me to create a credential on my smartphone first, and then let the credential travel to my tablet and my laptop as well. Right, so support for sync passkeys now is available in the platform authenticator, and technically it would also be available for the security keys, even though I haven't seen any real implementation of that. And technically, a passkey is just a discoverable FIDO credential, so something you can use without a step before that. So it's really the passwordless authentication. Looking at that, how FIDO works picture again, so what did really change? And this is an interesting observation here. Nothing really changed on that level. So you still see everything that you have seen before. The only thing that really changed is an implementation detail of the authenticator. So authenticator vendor could just implement a method to migrate or synchronize the keys, right? Potentially through a cloud service, but not necessarily through a cloud service, from one authenticator instance to another one. For example, from my smartphone to my tablet. This really changed a lot of the characteristics and did not require a big specification change, right? So we did some things to make that easier and to reflect that fact in the specifications. But in reality, this was just an implementation detail of the authenticator, which really made a big difference to that. Now, looking at the life cycle again, having the traditional FIDO really adding a lot of value for the re-authentication use case. Now we see that the passkey, the synced passkey approach also extends that benefit to bootstrapping new devices. You still need to use non-FIDO authentication as a way to authenticate before the first passkey is being created. That's a clear thing, right? That would be another topic to address that. Wallets will likely be used for that purpose. But bootstrapping new devices and re-authentication now are both addressed by FIDO, which really helps us to address the 90% use case, meaning the password replacement as opposed to only MFA replacement. Complex device management and user verification are practically kind of outsourced to the passkey provider, right? So the passkey provider takes care of that you as a relying party, which is interested only in a password level security, just a little higher, like phishing resistance already, right? So you do not have to take care of how users would migrate from one device to the other. Now, interesting aspect here, comparing FIDO with PKI, right? Sometimes people think, oh, you are using cryptography, public keys, right? So why isn't that PKI? So here's some differences. Let's walk through that. The first thing is, in the FIDO world, we really have the concept of an authenticator, where the authenticator itself has multiple components. And let's start with the view of the FIDO authenticator and the components of the FIDO authenticator, really, right? Which is a similarity, right? Both of those authenticators, right, contain keys, and they can be protected in software and trusted execution environments and TPMs or even in secure elements. But now we have some differences as well, right? Looking into the FIDO world, right, and at the differences, we see that FIDO is based on a direct trust model, right? There's the user that authenticates to a relying party, and there's no third party in between. Where in the PKI world, you have certificates which need a registration authority and a CA infrastructure, like the infrastructure, the I in the PKI world, right? So that is the difference between FIDO, direct trust, and PKI, the third party, the certification authority, if you will. There's a second one. If with the FIDO authenticator concept, it supports bring your own device or own authenticator model, where the attestation helps the relying party to understand the characteristics of that authenticator. Where in the PKI world, that doesn't really work, right? So it's either the smart card or the credential is issued by the CA and the hardware is provided by them, or you have bring your own authenticator, meaning I can buy my smart card and just create a certificate on it. But in that case, the CA doesn't learn the characteristics of that smart card and it might not even be one. Right? So that's another difference here. Another difference, in FIDO, we have a key which is tied to a relying party. So if I have account at bank 1 and another account at bank 2, I would already have two different keys, which are implicitly and automatically managed by the FIDO authenticator. In the PKI world, it was really designed to have three different types of keys, but they were shared across all relying parties. One key for signing, one for non-repudiation, and another one potentially for encryption. Yet another difference here. In FIDO world, only privileged components can assert the relying party to the authenticator, meaning it's either the browser or the platform, meaning the operating system itself, talking to the authenticator and telling the authenticator, oh, you're just browsing to bank1.com, or you are opening bank2 native app, right? In the PKI world, any native app would have full access and browsers would barely support that. And you would have to install third-party drivers or middleware, right, to get that. From a cryptographic perspective, we know that all the keys in the PKI world would allow you to sign arbitrary hash values, right? So technically it's an uncontrolled to be signed object, where in FIDO, we take in potential random challenges, right? Hash values from the outside world, but the FIDO authenticator would include that hash value just as a part of an of a to be signed object, a well-formed FIDO assertion, right? So FIDO always controls the to be signed object. It's not an arbitrary thing from the outside world, which means we don't need different keys for signing and non-repudiation. It's just one key is enough for that. Then user verification, the last one, dynamically used and asserted by the authenticator itself, where user verification in the PKI world is captured outside, like a PIN for a smart card, for example. It's a static method, and the smart card doesn't even know whether that was freshly captured from the user or not, right? Then there's dynamically used transaction confirmation display, where we have that in some FIDO specifications. In others, we are still in pull request open to work on that. But in the PKI world, there's no ability to really enforce the non-repudiation part, even though the key talks about that. But it's reliant on an outside component where no one knows what that component is. So just saying, there are several differences for good reasons between PKI and the FIDO world. The most relevant one, in my opinion, or apparent one, is the I in the infrastructure, right? That in PKI, that doesn't exist in FIDO. It's just public key cryptography based. Now, what do we think will come next? So we have an interoperable ecosystem for authentication. We have addressed the device migration, at least for unregulated markets. We have already implemented the user choice for credential providers, pluggable passkey providers as a key term here. We have expanded that to payments, secure payment confirmation. We are now working on the verifiable consent, right? That is one of the pull requests I just mentioned. And the next thing we expect to happen is to address device migration for regulated markets, where device-bound keys and attestation for that and things like that, device binding comes in and need to be addressed on a different level. And for the unregulated markets, we expect to see a convergence between wallets on one hand side and passkey providers on the other hand. And I recently did a talk at the European Identity Cloud Conference on that topic, to then reach an interoperable ecosystem for reusable identity, where it really gets easy to sign up to new accounts, right? And then do the device migration and the re-authentication in an easy way with robust security. And this is what I would call the e-promised land, right? This is the world where we want to get to, with robust security, very convenient for the users. So that is what I wanted to share. I think we have now some time left for questions.
Mike? Please, Professor.
Yeah, thank you. I have a question. One of the challenges in the phishing is it's a look-alike this one. Like if I want to interact with a bank, it looks alike because I don't check whether this is the real bank with which I am doing it, kind of a thing. But with FIDO, I am not understanding how that challenge is being taken care of.
Okay, very good question. Thank you for that. So let's walk that through. In a FIDO world, let's have a user that has a web browser, now opens bank1.com, right? And he thinks he opens bank1. Maybe he clicked on secure-bank1, which is a man in the middle site, right? I think that's a scenario you're describing, which looks exactly like the bank1.com website. Today, I would enter my password and even the OTP, and the man in the middle would say, thank you, and now owns the authenticated session. In the FIDO world, it's different. In the FIDO world, the browser would talk to the operating system and say, okay, I want to do FIDO. And by the way, the relying party ID, right? The URL I'm talking to is secure-bank1.com. And now, different from human beings see secure.-bank1 and say, okay, that's even more secure than bank1.com. And it's bank1 is included, right? And they might think it is bank1, right? So whatever you do, you are really convinced this is bank1.com. And the FIDO stack would just say, no, it's secure-bank1.com. Do we have a credential for secure-bank1.com? Very strictly. And the FIDO authenticator would say, no, I don't have a credential for securebank.com. And especially the bank1.com credential will not be used for that. So from that perspective, the ability that there's a direct browser integration, right? The check of the relying party ID happens in the platform itself and does not rely on the user to check whether the URL, right, is really the bank and the certificate matches and all that stuff. This has been automated inside the client-side implementation of the FIDO stack in the platforms like Windows, iOS, and Android, and it's also being implemented in all the web browsers today. So really that the notion of that private key being tied to the relying party ID or the URL you are talking to, that makes a difference, and that makes it phishing resistant in this case. By the way, NIST SP 863 calls that verifier name binding, and that is exactly that thing that FIDO provides. On a second level, right, there are even more things like token binding, other methods you could use, but that's a more detailed discussion. But large scale, it's really that verifier name binding we are doing in FIDO that helps against phishing attacks.
Is there an overhead or a performance degradation?
No, not for the verifier name binding. Right, so that is really, this is just part of the system, right? What platforms do anytime, right? They just compare these two strings and then they say, oh, that works, right? So that there's no performance degradation. There is a difference, however, if you compare to passwords and OTPs, where you just send a bearer token from the client to the server, as opposed to in the FIDO world, asking the server for a random challenge, do a computation on the client side, and then send it back, right? So there are some differences there, but overall, FIDO is a very fast authentication. And if you measure the authentication time that you get in practice, FIDO is much faster than existing authentication protocols today, like passwords or OTPs. And it's good statistics around that. Does that answer your question?
Yes, he agrees.
Great, thank you.
Okay. Any other question? No, thank you, Rolf. Thank you so much for connecting with us and making us aware about this FIDO authentication.
Great.
Thank you.
Thank you for the invitation.
So next we'll start with our first paper presentation session. So first of all, okay. We're just waiting for our next session chair. So I request Sri Ram Prakash Pandey, Scientist E from Office of CCA, to be our session chair. So at first I will request Dr. Abhay Jacob, Scientist F, CDAC Bangalore, to felicitate our session chair.
So now the paper presentation for this session. The title of the paper is Demonstration of Secure Key Management Solution with Use Case in Permissioned Blockchain. The author is Ms. Geeta. Please.
Thank you, sir. Good morning to one and all present here. I am here to present our paper titled Demonstration of Secure Key Management Solution with Use Case in Permission Blockchain, which is co-authored by Ms. Kausalya, and it is mentored by Dr. T.R. Reshmi, scientist and as well as the principal investigator of this particular project, UBF at SETS Chennai. And this is funded by METI as a consortium project, and it has been launched as a Vishwasya National Blockchain Framework 2 days before by METI. So the outline of the presentation goes like this. So introduction to need for a HSM or a key management solution in a permissioned blockchain network like a Hyperledger Fabric, background of HLF and the public key crypto standards that we use for integration with the HLF, and the basic operations of a fabric, the permissioned blockchain that need a private key or a PKI infrastructure, the proof of concept for our implementation, the recommendations in integrating the HSM with any distributed applications like blockchain, followed by conclusions and references that has been used for this. So in any PKI infrastructure, the private key is an ownership of any digital asset, and it has the control over any digital asset that we placed it. So the compromise of the private key may have an irreversible security losses. So the identity and access management system that we claim to be secure by means of using a PKI infrastructure can be irrelevant when there is a compromise of the private key. So the secure storage solutions or secure key management solutions for the private key like HSMs, encrypted vaults combined with regular or strong encryptions, access control mechanisms are essential to prevent the compromise of the private keys. This particular study investigates the security of PKI entities in an extensive distributed applications like blockchain. It features a prototype that integrates an indigenous CA for a Hyperledger Fabric with a hardware security module, and the demonstration has been done with a secure software module and emulation of a practical HSM. So before we just proceed with the detailed discussion of the integration, we just want to make clear one point that as a part of a national blockchain framework, we had 2 products that has been delivered. One is an indigenous certificate authority that has been developed for a Hyperledger Fabric, and second one is this particular thing, a secure key management solution for the same fabric. The Hyperledger, which is a permissioned blockchain framework, comes with its own Fabric CA component. So the SETS has replaced the Fabric CA component with an indigenous CA, custom implementation of their own PKI infrastructure in accordance with the blockchain fabric, and we have delivered it as a first deliverable for the national blockchain framework. So the background of Hyperledger or a permissioned blockchain framework. So Hyperledger is widely used to private or a permissioned blockchain framework with a flexibility in application to different varieties like starting from e-healthcare, IoT, and to larger number of applications like supply chain management, land record, health management systems, etc. HLF access to the distributed ledger, which is an immutable component of any blockchain fabric with a valid crypto credentials. That is primarily a public key infrastructure with a public and private key, with every node has been validated and verified to a digital signature component and X.509 certificate. The identity and access management system in HLF is handled by a Fabric CA component, which provide a PKI-based crypto credentials and keepers to every nodes that enroll inside your fabric. As a part of a national blockchain service, Fabric CA in the HLF component has been replaced by means of an external PKI-based CA. A secure key management system for HLF using this indigenous certificate authority is our point of study. Before we just move on towards the integration part, we will have a brief introduction about the secure key management option that has been available as in terms of crypto wallets. The crypto wallets are digital tools that allow us to store private key and do transaction in a secured manner or a client secure manner. So it is a combination of a public address and a private key. So the wallet in general can be classified on basis of three main criteria: a connectivity, nature of physical existence, and control over wallets. The connectivity, it is termed as a hot and cold wallets. The wallets that are connected or actively connected towards an internet infrastructure is termed as a hot wallets, and they are flexible to do everyday transactions. Cold wallets are traditionally an offline wallets, and they are not connected to internet. They are isolated in nature. Cold wallets are claimed to be more secure because of their isolation nature, but yet they are not flexible for an everyday transaction. Based on the physical status of existence, they may be classified as hardware, software, or paper-based wallets. Hardwares are typical HSMs or the smart tokens or smart cards that we use for a secure key storage. Software-based wallets are a secure key management solution, a hardened key management application that offer a secure key storage in a mobile or desktop or computer-like applications. So they yet offer a storage inside your file system, a local host file system, but yet they are secure in nature by means of an AES-128 wrapping or encryption, and yet the keys are stored in an object format. Any access to the private key without a PIN may create a segmentation fault or a dump. And the paper-based wallets are a QR code the QR code or format that store the physical the private key. The physical damage may of course tamper your QR code, and yet you will not be able to retrieve your private key. And the last is the control over the wallets. It may be a custodial or non-custodial wallets. When the user who just stores the private key, or an enterprise which stores the private key, when it has a complete control over the key storage as well as the slots, it is what we call termed as non-custodials. A custodial wallet, there was an enterprise which is holding an HSM, and there is a slot that is provided to you with which you can able to store your key, and yet you will not have the control over the entire HSM. There was a controlling authority. So the HSMs may be this particular custodial wallets may be a HSMs, or hardware-based wallets, or a software-based wallets, or sometimes a network or a cloud-based HSMs that may be hosted online. So the public key cryptographic standards, we specifically talk about one standard, which is a PKCS 11 interface, which is also called as crypto key API. So why the crypto key API is that? So PKCS 11 is a tool, or it is a utility, the cryptographic token interface standard that provides an application programming interfaces for the devices that holds the cryptographic information. So the default HSMs or vendor-specific HSMs comes with an interface that has been developed, which is a PKCS 11 API that has been enabled. The default Fabric CA component inside the Hyperledger Fabric also comes with an option to enable the PKCS 11 binaries, by which the file system storage can be changed to the HSM or the SSM, the secure software module. In the proposed work, the HLF uses an external pluggable CA, which is also a PKI based with its custom implementation of an ECDSA. Hence, to integrate our CA within the HSM or a secure software module, it is necessary to enable a PKCS 11 binary or a PKCS 11 interface in this particular CA. So the PKCS 11 libraries will be modified. They have been modified in order to use the custom CA implementation. The right-hand side part of the code snippet indicates the flow with which you have to touch your PKCS 11 binaries when you are attempting to use a custom implementation of your any cryptographic algorithm, whether it may be a symmetric or an asymmetric cryptographic algorithm. Yet you have to integrate your algorithm into your HSM. So this is the way in which you have to touch your PKCS 11 standard. So the two major operations of a hyperledger fabric which extensively use the private key are the enrollment process, an initial enrollment process, and a transaction proposal and a signing. The diagrammatic representation or a flow diagram of an enrollment process has been presented at the right hand side part of this particular slide. The enrollment process needs a CA for generation of a crypto credentials. The private key will be stored inside your HSM vault itself, yet the public key will be retrieved outside the wallet, because there are a lot of verification process that will be happening, and every strike inside a HSM may reduce your efficiency, since blockchain is a distributed application with geographically disseminated nodes across your country, and yet you can't go for a centralized vault that have a lots of it. This may reduce the efficiency. In the same way, after an enrollment has been done, the digital verification, the client application generates a transaction proposals, which includes the details about the transaction, such as a chain code or a smart contract, and it will be submitted to the endorsing peers, nodes inside your hyperledger, and they use the private key to just verify whether this transaction is valid or not. They will sign, endorsing peers will sign the transaction using the private key, yet the private key will be retrieved from the HSM vault, and the transaction may be added towards, if it is endorsed and it is a committed, it may be ordered as a block inside your blockchain framework. So the two main operations, generating the key pairs inside the HSM, getting your public key out from the HSM, and getting a certificate that CSR generated, certificate signed inside your HSM, and a transaction proposal and signing. In normal PKIA infrastructure or an operation, an X.509 certificate authority, it is enough to generate a CSR, get your certificate, X.509 certificate signed, and it is a digitally verified certificate. When the certificate is revoked, when there is a CRL, you just again go for your, you generate your keys, again go for a certificate. But the case of blockchain, it is little different. Apart from the certificate signing, the traditional place of certificate authority, it is a nature for a HSM to also support the process of transaction signing and committing. So the proof of concept for this implementation has been done with a secure software module or a software security module. We used an open source implementation of a soft HSM and emulation of a hardware security module. A soft HSM provides all means of cryptographic security for your private key, apart from the physical security that is offered by your HSMs. The default network configuration of HLF with two organizations, one ordering service node which is responsible for ordering your transactions inside your block, two peers, one will be an endorsing peer which endorses your transaction, and a committing peer which commits whether the transaction is correct or not, and one certificate authority which is an external certificate authority which is provided by SITS. The soft HSM, the CA that we have developed and the Hyperledger Fabric, the CA that has been integrated into a Hyperledger Fabric has been upped or hosted as a Docker container service for security purposes and continuous running. So we hosted the CA as a Docker, which is an independent Docker. So to just enable the integration feasibility, we also tried hosting the secure software module, that is a software HSM is integrated with an external CA, and it will be run as a separate Docker container. The HLF, the Hyperledger Fabric, which will be loaded as another Docker container. A client who want to enroll may be attached to any one of an organization. An organization will have its own certificate authority attached to an SSM, and which will be responsible for generating all the crypto materials and operations. So the integration has been attempted with the soft HSM as a Docker along with its indigenous certificate authority of the SITS. So we just finalized some recommendations based upon our study that we have done. So we just finalized some recommendations for enrolling the hardware security modules. So the HSM is actively for a Hyperledger Fabric or a blockchain-like application. Apart from generating a CSRs and certificates, your HSM has to do a little more job. Of course, the HSM is actively involved in both enrollment and the transaction signing processes. So the performance of the Hyperledger Fabric, a blockchain, the number of transactions that has to be committed per second, maybe in terms of 10,000 in case of a fast fabric or a scaled up fabric. So the performance may vary depending on the firmware or a HSM version that has been used for an integration. When you are developing a custom crypto implementations and you are using an external certificate authority that has to be integrated with your HSM or any soft HSM, so the cryptographic standards of your implementation may vary. So we recommend you to modify the PKCS 11 certain binaries or libraries to incorporate your custom digital signature algorithm or your custom public key infrastructure. This overhead, of course, may reduce, this modification, of course, may induce some overhead in your key generation process, since there was a 2-layer of abstraction that you have to cross to generate a key inside your HSM. So this may introduce some overhead. The optimization of CA may yield a better result. So the conclusion, the feasibility of integrating the HSM into the permission blockchain framework such as HLF with the custom implementation of CA has been attempted. The POC of implementation with the software emulation of a HSM has been hosted as a Docker service and it has been tested. So the private keys has been generated and stored inside the SSM, and the CA based crypto operation has been validated inside the SSM. The potential limitation in terms of scalability of slots for HSM in for applications like blockchain has to be validated in the when it is hosted as a network service. The complete performance benchmarking and optimization of crypto operations in custom CA based upon the service for which the blockchain is hosted must be accommodated in the future. So these are the references that has been used. The reference of an indigenous CA that has been used for a Hyperledger Fabric is again a presentation that has been used that has been done in a PKIA 2023, and it will be available in the proceedings. So thank you. And queries?
I have a question.
Yes, sir.
You know, when you have a overhead, it has an impact on the underlying consensus algorithm, which leads to unfairness. So technically, these things cannot be done in an isolated manner at all. The most important thing is the consensus algorithm in the blockchain platforms. In fact, whenever you try to enhance the performance, it fails because a consensus algorithm will not work like that. And also, it's very important to see it in a totally integrated way, because nowadays the blockchain platforms have more unfairness problems rather than fairness.
Thank you, sir. Actually, we can understand that there was a large overhead that may happen at the consensus part of an algorithm, and we want to be, as I stated in the starting of a presentation, as a part of the deliverable, we are concentrating on a certificate authority and the secure software module that we have to deliver for a national blockchain service. And the integration has been attempted, but the performance benchmarking as a blockchain as a service is still under study. We know this may create some overhead when there is a centralized HSM that has been used, that must be used for a consensus mechanism of transaction. So we understand that, but it is still under progress and as under study, sir. Any other questions? Yes.
See, it's a very good presentation and very good work initiated by SET's team. My only query is that why do you want to modify the PKIA 11 libraries? It has some standard format, and it has to be when you do an internal CA operational activity or custom designing CA for Hyperledger Fabric. So two things, the drawback is one is the overhead.
Yes, sir.
And the more modification what you're planning to have executed in the PKIA 11 standard, what are the drawbacks you have been facing it by overhead which you have been facing it for the computation time?
So the first thing is it induces some, we have to agree that it induces some overhead. The benchmarking or an optimization is an understudy.
If you do some modification overhead, it's okay. But what are things you are going to achieve out of that overhead?
So the first one is we just started our emulation with a secure software module or soft HSM, which uses an OpenSSL, which has two options: to use a bolt-on SSL or an OpenSSL based crypto implementations. And your HSM or a SSM will just connect you to an external world or any application. If it is not a traditionally CA, it will connect you to any external application only by means of an interface, a cryptographic standard, that is a PKCS 11 tool. So the PKCS 11 tool or an OpenSSL itself, they have a direct communication. They can able to understand it. But we are not using an OpenSSL operations for a key generation or a bolt-on SSL operations for a key generation. So we have a plug-in interface. So we have our own methodology of key generation outside. So the way
this overhead you are talking about the key increasing the key generation process
and the The CSR and the certificate generation activity, sir. As a whole, only the X points, we are not talking about the use of private key for a transaction proposal and signing. That is a different activity that don't have any touch with an OpenSSL level operations. So the first phase of getting your digital identity signed from our CA. So that requires a modification of the PKCS 11 binaries in accordance with our flow. We have our implementation that has been FIPS validated. So we have an option to add our custom implementation into an OpenSSL library such that PKCS 11 can able to understand our implementation. So we have our next, in the next session, we have paper
provisioning you are introducing in the hyper HLF so that this PKCS 11 has to be modified.
Sir, when you use a Fabric CA, it don't have to be modified. The Fabric CA has set up in such a way that it understands the OpenSSL and PKCS 11 operations. So we just replaced the Fabric CA. That is, we made it as a default disable it, and we just enabled an external pluggable CA for a Hyperledger Fabric. So it just offers. It just wants us to modify that such that we can able to accommodate our CA seamlessly into the HLF operations.
So it means you are linking towards the internal CA operation only for the PKCS 11 standard, right?
Yes, sir.
So that is the only achievement you are planning to do with the HLF, right?
Yeah, so make sure that your hyperledgers understand your external CA, but in a standard format, the PKCS 11 format. So that must be a standard. So suppose if the external CA has been replaced and some other CA is also placed, there is no problem. So we just modify your PKCS 11 library in the way that we have given us. So you can enable your you can enable your certificate authority into your blockchain.
Okay, thank you.
Any other queries? Yeah, thank you, and thank you for the opportunity.
Thanks, Ms. Geeta. It's a very nice and a knowledgeable presentation of the paper. The QA session shows that the authors who are presenting before lunch will have to reply the QAs in a very, very smart way. The authors will be relaxed after lunch, I believe. The next paper presentation is, the title is Role of PKI for Securing AMQP Communication. And the author is Mr. Sanjay. Please. Yeah.
Good morning and thank you. My paper title is Role of PKI in Securing AMQP Communication. So here what exactly we have done, we have explored various attack vectors of AMQP protocol, and then we demonstrated how AMQP can be targeted, some of the attacks what we have demonstrated. And then finally we suggested how PKI will be involved here to secure this particular AMQP communication. So this is the agenda of next 10 minutes. I'll talk about AMQP and then what are the various threats which are actually involved in AMQP communication, followed by the attacks which we have performed here in this particular paper, the dictionary attack, DOS attack, and MITM attack. And then I'll focus on how PKI can actually mitigate those attacks. And finally, we'll be showing what challenges which are there with respect to AMQP, and we can conclude our this particular talk. Now, if you see, all of us, we are using internet heavily. Almost 8 hours we are spending browsing internet. Now, the way internet has reformed the world, we cannot hardly envisage our life without it. Again, if we see that we are living in the era where various objects are interconnected, and these objects are uniquely identifiable. They can actually sense, they can actuate, they can communicate without any interaction of human. So if you see, we have around 62 billions of IoT devices in the world, and which is outnumbering humans. Humans are around 8 billion. Now, one study says that we have around 150 billions of IoT devices by 2030. Now, if you talk about AMQP, we have application layer protocol, which does device communication. And we have a lot of protocols like HTTP, we have CoAP, we have MQTT and AMQP. And if you see about AMQP, this is the protocol where actually it uses publisher and subscriber model. Like if you browse YouTube, the YouTube has one publisher, and the people who is actually browsing that particular channel, they can see. So here, same things, same concept is used here in AMQP communication. You have one publisher, and then you have a consumer. In between, we have something called a broker, which will actually exchange the message between queue and like various queues. Now, this particular slide shows that how the AMQP can be targeted. What are the various attack vectors of AMQP protocol? Starting with if AMQP is not secure, like default configuration will be there with the AMQP, right? So in that, a lot of attacks can happen actually. I'll be showing what we have done with this kind of default configuration, where we are using an RabbitMQ application, and that was default configuration was done on that, and then we performed some dictionary attack. Again, if you see, we have something called interception and manipulation of messages with respect to AMQP attacks. So here actually what we have done, we have performed an attack called MITM, man the middle attack, and we shown that how the AMQP communication can be targeted. So from broker to say publisher or subscriber, we can get the communication detail actually very, very easily. And again, we have demonstrated one more attack called denial of service. So how this AMQP communication can be broken, can be made unavailable. That also we have shown. And apart from that, lot of attacks are there with respect to this particular protocol called AMQP. As I told you, we actually performed 3 attacks mainly. One is a dictionary attack, other is a denial of service attack, and man in the middle attack. So as I told you, here we used AMQP application, which is actually called RabbitMQ server. And on that RabbitMQ server, this is the default configuration which we have done the setup. And on that, actually, we have performed this dictionary attack, and we got some username and password from that AMQP, that particular RabbitMQ server. And again, we performed DOS attack, where we have used one Kali Linux tool, Zero Exploit. Using that, we performed this DOS attack, and we made this particular application unavailable for the user. And we also performed MITM attack using something called ARP cache poisoning. And there we could see the message which is going between a broker and actually subscriber. So this is the first attack how we have performed here. As I told you, we use something called Kali Linux. So in this dictionary attack, the RabbitMQ server was there, which we have configured on one of the system. And then on attacker's machine, what we have done, we did the scanning on that machine, and we got to know that AMQP actually is running on the particular machine. And we used Nmap for seeing what the version this particular RabbitMQ is there. So once we got to know that, we got to know that these are the default configuration of RabbitMQ. These are the default username and password which can be targeted. So we created one Python script or Python program. Using that, we can perform this kind of dictionary attack. And once we have performed the attack, we've got to know all the users which are part of that particular RabbitMQ server. Now, next is DOS attack, how we have performed here. As I told you, we used Zero Exploit, one tool which is by default installed in Kali Linux. And the first thing what we have done, we started executing that tool and then scanned for the devices in the network, which was shown here in that slide. And once we got to know this is the target, we set the target and we use one module called DOS module as a part of this Zero Exploit or Zero Exploit tool. And we sent around 191 lakh packets to that particular RabbitMQ server, and we got to know that that server stopped working, right? So DOS attack was successfully performed. And the third attack, what we have demonstrated in our paper is man-in-the-middle attack. So here, as I told you, we use ARP cache poisoning. And in that, actually, one tool was used, EtherCap. And that EtherCap tool is by default then as a part of your Kali Linux. And once we executed the tool, we set two target. One is broker and other is publisher. So we wanted to capture the communication between broker and publisher. And we set one parameter called sniff mode connection. And then we launched this attack. So once we successfully launched this attack, all the traffic between, say, broker to publisher, we were able to see. Right, if you can see in this right hand side image, right? So hello world, which was sent from, say, publisher to broker, we could see in our machine. So we successfully performed this attack, compromising the integrity and confidentiality of this AMQP communication. Now let us see how the PKI will mitigate those kind of attacks. Not all, even DOS, we know that nobody can, DOS or DDoS we can mitigate, but still some of the attack using PKI can be very easily mitigated. So as we know that AMQP is using actually SASL and TSL for encryption and authentication. So integrating PKI into AMQP protocol significantly strengthens its authentication mechanism. So by incorporating digital certificate and cryptographic protocols, PKI provides a robust framework verifying the identities of the communication entities. So this will ensure that only trusted parties can establish the connection, thereby enhancing the overall messaging system and safeguarding data integrity and confidentiality during the transmission. Here, the certificate-based authentication, where we are using X509 certificate, verify the identity of each and every component of this AMQP communication, like broker, you have publisher and subscriber. So as I told you, TLS is used here for encryption and authentication as well, whereas SSL is used here for actually additional authentication, which is called Kerberos and TLM. Now, what are the various challenges which are there here as a part of this AMQP communication to secure? If you see, securing IoT communication using AMQP presents several challenges due to the nature and requirement of different IoT devices in the network. Again, these devices has limited power, limited memory and battery life, which make it them more vulnerable to physical tampering and unauthorized access. Again, we have the different kind of devices from different manufacturers, which has own level of security and capabilities. So managing this kind of say task like firmware update, patching, and all is a little bit challenging. So in this, we are concluding saying that our paper actually focuses on what is the role of the PKI for securing this particular AMQP communication. And here we have demonstrated attacks, various attacks. We have identified some attacks, and we have done the demonstration of 3 mainly attacks. And in this, these are the references which I have used. Yeah, so any questions? Yeah, if no questions, then thank you very much.
I will request Dr. P.V. Anand Mohan to felicitate our session chair with a memento. Dr. Anand Mohan, sir. Sir.
Good morning to all of you, ladies and gentlemen. Ashish Banati, sir. I don't know. Fine. I request all the CCA members and CDAC Bangalore members to be near the dais. There's a small announcement from our side. I request Shri Arvind Kumar, sir, Controller Certifying Authorities, New Delhi, to the dais. I request Dr. S.D. Sudarshan, sir, Executive Director, CDAC Bangalore, to the dais. So the occasion is a signing of an Memorandum of Understanding, MOA, between CC and CDAC for establishing and operating the disaster recovery site for the Controller of Certifying Authorities. I request the files to be given. I request CCA members and the CDAC members, Praveen, Murli. So now the signing process being completed, we request you to exchange the MOUs. And please give a big round of applause, please. Yeah. I request the CCA members and CDAC members to be on the dais for a photograph. Ravi.
Yeah, namaste all. Very good morning. I think, thank you, Professor Venumadhan, sir. Sir, since the inception of the data center to keep the root certificate and the subsidiary certificates, being a critical infrastructure, there was a need for having a disaster recovery site. So the main data center is at CCA Delhi office. The DR site was at CDAC Bangalore. So it is the process going on since inception. And it follows all the protocol both in letter and spirit since it has been done. At the same time, this MOA governs a little more than just the DR and the data center part. This allows us to work a little bit on the creating a awareness part for the audience, public in general, and then how to enable the ecosystem to grow by doing certain annual publication and report of how other countries are doing, the maturity level of our PKI in the country. Also developing some tools for both for learning purpose as well as testing purpose. They are all part of the MOA, sir. And being an MOA, it has a time limit. So every 3 to 5 years, we sign and exchange again. So that it is basically a continuity, revalidated, reinforced with a new target date for validity purpose. Because this is the basis by which CDAC also we have specifically trained certified members by CCA. They go through the standard process of onboarding. So it is both the technical process as well as the background and other criteria that is needed to operate such a critical infrastructure. And also an agreement that these members are available at least as we speak 2 out of 5 anytime 24/7. So these are the obligations we have so that the uptime is guaranteed. So several things that ensure not only the PKI CCS root certificate data is safe, but all the processes are continuously followed, and there is a quarterly review of the process that happens, and annually they also get an external auditor to check the compliance similar to the CAG. All these things we have done, sir. So this is the kind of a baseline framework which gives the, so to say, the tooth for our activities. The other things come on project basis, this one. That is how it happens, sir. So that was the background. Thank you for the question, sir. So we could explain. Sir, you want to add anything, CCA, sir? Okay, next. So today was the occasion to renew. Thank you.
So we will start with our next paper presentation session. So for this next paper presentation, we have our session chair, Sri Samsuddin Khan, Assistant Controller, Office of Controller of Certifying Authorities. I request Sudarshan sir to felicitate our session chair. Thank you, sir. So you can announce.
Hello. In this session chair, I request Ms. Karthika VATL for her topic like distributed estimation based on PKI for in-vehicle network security. So I request Ms. Karthika.
Good morning, everyone. I'm Karthika from CDAC Bangalore, and this is a collaborative paper with TVS Sensing Solution, Kalasangalingam Academy of Research and Education, and CCA. So as we all know, in-vehicle network comprises of at least 70 plus ECUs and various other components. And as the cyber physical systems are evolving and software-defined vehicles are evolving, there is going to be more electronic and software components within the vehicle. There is a need for having lightweight cryptographic schemes that has already been highlighted in various previous presentations as well. But the identity of these components also becomes important. In this work, what we have attempted is to use the cyber physical variables that exist in these components, which are dynamic, which keeps changing, and how can we leverage that in order to ensure the layer of security. So let us consider the scenario. I have a network of components A, B, C, and I have M, and M keeps sending data to A. And M may be, can be malicious, may not be malicious, but A wants to check why is this device is sending me this data. So how do I ensure this kind of, can I provide a mechanism? So one is M can be a spoof, or it may send some garbage data just to do a denial of service. How can I trust M? So here microcontrollers that are there have very limited hardware, and also the algorithms has to be fast enough. And we have attempted to use cyber physical data and then proposed a distributed estimation based technique. What is cyber physical data? All these components that are going to be there in a vehicle, it is going to store some data which is very specific to vehicle at that time point. It may be temperature, speed, odometer value, which keep, or many other variables that are there within the vehicle. Each of these variables are going to change from one time point to another. Can I use this variable, which is dynamic, in order to establish this trust between these nodes in the network? For this, we use this concept of relative measurements. At any given point of time, the node will know its relative measurement with its neighboring node. So let us consider there is a node N1, N2, and N3. And then node N1 is a neighbor of N2, N2 is a neighbor of N3. So all three of them, let us assume they have temperature values, and node N1 ranges from 0 to 40 degrees, N2 ranges from 0 to 80 degrees, and N3 from 20 to 30 degrees. And they know how they are relative to its neighbor nodes. So N1 knows that N2 can either have a value that is equivalent to N2, right? So it is either equivalent to itself, or it can have a value which ranges between 0 to 80 degrees. Because of this range that they know that, so N1 knows that it can be either equivalent to N2, or it can have a value which is at most that it can be vary between 0 to 80. Similarly, N2 knows its relative measurement to N3. So these relative measurements are used for establishing this trust when I'm in a doubt. Now this relative measurements, I always know, so if I have a neighbor, I will always know that I am +2 ahead of that neighbor, or -2 below my neighbor for this specific data. So I can store multiple data. I may have temperature data, I may have speed data, I may have many such cyber physical variables stored in me, and I always know relative to my nodes in the nearest neighbor, what is my variable relative to that particular node. So we use this graph structure that exists within this network and create this probing system around these cyber physical variables. So for example, I'm not going to use just one variable here. I'll be using a group of variables. Like I create a vector of variables, maybe speed, temperature, and timestamp. And I can also define the probing order. So if there is a node M which is trying to connect to me, then I can I can ask my trusted root. So there is, I'm introducing this concept of trusted root, which many frameworks do. But how is the trusted root going to establish this mechanism in this relative measurement scenario? So that is what we have worked out over here. So this probing vector and the probing order is sent to my trusted root when a node M tries to connect to me. And trusted root will tell me that, no, there is a node E1 and that node is relative to M in this certain fashion. So you can ask node E1 for its relative measurement with M, and you can ask M and compare its values, whether it is giving the same thing. If so, you can trust M. So this probing vector and probing order, I can keep changing. So I am E3 and I am sending a probing vector and probing order to M, and I can change the probing vector and probing order, and I can send it to E1 as well. So and along with M I am sending. So what E1 will give me is that the relation of it corresponding to M for that probing vector and order, and M also will give me this probe values, and this comparison will happen if E1 is a trusted node. So there may be a case I don't trust E1, I don't know who E1 is. So how do I go about it? So if E1 is not a trusted node, I can keep asking the trust root that, you know, possibly give me the next hop neighbor for E1 who I may trust, or the next hop. So this can keep continuing till I find a set of trusted nodes from this my root. So if T1, T2, T3 are the trusted nodes that I get, I can again choose whether T1 or T2 or T3 should be used in this as a path to go and probe E1. So this way, one more layer. So this can also be selected dynamic, so that one more layer is added into this security for probing the malicious node. If there is another scenario where the trusted root may inform that I don't have any information about him, I don't know who are the neighbors of him. So that time, of course, this node may be malicious. So we may have to do other PK mechanisms over here. Now this distributed estimation, as I was saying in the initial, the relative measurement, it's not a linear equation. It will be a vector of values, and it is a matrix that will be formed based on the network, the trusted network that is already existing within the vehicle. So this is not a linear complexity problem which can be solved easily. So that adds the layer of difficulty in cracking what the challenge response mechanism that goes within this network. The implementation of this concept, to prove this concept, we have done with MQTT by mimicking these ECUs with node MCU modules, and using this one tested node will be there, which will have this graph, entire graph of the other nodes within the vehicle, and the subgraphs or the paths will be formed in dynamic fashion as and when a challenges or a probing vector is sent to the trusted node from one of those ECUs. Yeah, so this concludes my presentation. Any questions we can address this.
So there are two aspects in the automotive electronics.
Yeah.
One is time
Yes. Correct.
Time synchronization is one of the most important things. Like if you look at flex ray protocols and things like that, if without doing that, if you say a vector, the time will differ. Without verifying the time synchronization, nothing will work.
A timestamp is also one of the variables in that vector. So I will ask for its relative measurement at a certain timestamp.
You have to have strong synchronization.
Sure, right. We will look into it.
Any other questions? If else, thank you for the opportunity to present it. Thank you.
Okay, thank you, Ms. Karthika, for your presentation. Now I request Mr. Abhay Jacob, and his topic is approach to post-quantum cryptography validation. So over to you, sir. Is online now? Yes.
So, good morning, everyone. So today our paper is topic is approach to post-quantum crypto validation. So here we are just talking about how to validate post-quantum algorithms. What would be our approach as such? So we are working in the crypto module validation lab. So in the post-quantum PKIA project as such, so we will be validating the post-quantum algorithms. So I'm Smita and Dr. Abhay Jacob. Together we are presenting this paper. So this is my agenda, introduction. Next, I'll be discussing about the brief introduction I'll be giving about NIST FIPS 143 ISO 19790. Crypto module validation process and crypto algorithm validation process, post-quantum algorithms, and MLKEM crystal Kyber. What are the parameters? What are the auxiliary functions? Kyber PKE, Kyber MLKEM, and test procedures, some validation reports which we have generated in our lab. So NIST, under NIST, we have 142 validation process was carried out for crypto module validation as such. So this includes validation for crypto module, including hardware, software, or firmware for any US agencies. So now this one NIST has moved to 143, which aligns with the ISO 19790. So we are also adapting to the ISO 19790. So from now on, we will be validating the crypto modules with respect to 19790. And under FIPS 143, which supersedes 142, which aligns with 19790, there are 11 cryptographic security areas. So first one is cryptographic, like when we validate a module, we have to validate the module with respect to these 11 security areas. So first one would be cryptographic modules with specification, cryptographic module ports and interfaces, roles, services, authentications, software and or firmware security, operational environment, physical security, non-invasive security, sensitive security parameter management, self-test, life cycle assurance, and mitigation of other attack. So if a module has to pass ISO 1970, it has to comply to all these 11 security areas. And the relevant ISO standards for crypto module validation is ISO IEC 19790. So this talks about the security requirements for cryptographic modules, and ISO 24759. So this talks about the test requirements for cryptographic module. So these are nothing but test requirements in the sense what exactly the lab has to do, like what are the information vendor has to provide to the lab, and what the lab tester has to, how he will be operating the modules, like how he will be validating the modules, all will be explained in this ISO 24759, and both the vendor come tester in the lab has to follow this standard. Basically, this is called the derived test requirements. And we have for crypto module validation, prerequisite is crypto algorithm validation program. So in this CMVT lab, it generates some test vectors. They share the request file, which we call, which is an input which should be given to the module, and output, which in the form of response file, has to be generated by the module. So this request file will be shared to the vendor. He will pass the request file to the module. He will generate the response file, and he will share to the lab. So we will have the answers for the request file which we have sent to the vendor. So what we will do is we'll compare with the response which is there in the lab with what vendor has sent to us. If it matches, then we tell the vendor he can bring his module to the lab for validation. So this is how the process goes on. So this is how the communications happen between CMVT lab and the vendor. CMVT lab sends the request file to the vendor, and vendor in turn sends a response file to the lab. And expected response file, which is compared with the received response file, and if it passes, we'll ask the vendor to bring it to the lab. And under post-quantum algorithms, after 2016, NIST started call for quantum algorithms, as we all know. So after round 3, it selected 3 algorithms. So NIST has finalized FIPS 203, 204, and 205. So FIPS 203 is for MLKEM, that is Crystal Kyber, which is a variant of Crystal Kyber, and MLDSA, which is Crystal Dilithium, which is based on Sphinx, and SLDSA. So today I'll be talking about the Kyber algorithm. So this MLKEM is derived from the Crystal Kyber KEM, and it is a part of Crystal suite, that is cryptographic suite for algebraic lattice suite. So it uses module learning with errors over polynomial rings, which is represented as ZQ of x and x to the power of n plus 1. And for Kyber, n and q are fixed. That is, n is 256 and q is 3329, and it is standardized into 3 parameter sets. One is MLKEM 512, MLKEM 768, and MLKEM 1028, and it falls into the NIST security levels 1, 3, and 5. So it corresponding to AES 128, 192, and AES 256. So these algorithms are designed to ensure long-term security even against future quantum computing threats. So this is the basic key encapsulation mechanism. So here we can see Alice and Bob. So Alice, Alice will use the key generation algorithm and generate a decapsulation key, that is DK, which is private key, and encryption key EK. So EK encapsulation key will be shared with the Bob, and Bob will use the encapsulation algorithm. He will generate one shared secret key K and ciphertext. This ciphertext he will share with the Alice. Alice will use the decapsulation algorithm and generate the decapsulation algorithm and some random parameters and generate the shared secret key. So at the end, this K and K dash should be same. So without actually sharing the key, they are able to generate the shared secret key, similar shared secret key on the both the sides. So this is how the basic KEM works. And for Crystal Kyber algorithm, there are some parameter sets like for Kyber 512. NIST level 1, it is N is 256, Q is 3329, K is fixed to 2, eta 1 is 3, eta 2 is 2, DU is 10, and DV is 4. Like this, these parameters are fixed. This has to be used when we go for Kyber 512. These parameters has to be used. So when we use this, we get the encapsulation key in bytes as 800 and DK 1632. Cipher as 768, and shared key will always be 32 bytes. So K specifies the sizes of the vectors in PKE generation, which is denoted as S and E, and also the size of matrix A cap, the vectors of R, E1, all this are derived by the parameter K. And eta 1, it specifies the binomial distribution for generating specific vector S and E during PKE generation, as well as the there is a random R parameters to generate that also eta 1 is required, and eta 2, it specifies the binomial distribution for generating particular vectors like E1 sample vectors E1 and E2 in PKE encryption. And DU and DV, it specifies the input for operation like compress, decompress, byte encode, byte decode, which are utilized in PKE encryption and decryption. So there are some auxiliary function which are used in Crystal Kyber, like functions J and S, which is nothing but the SHA, basically SHA is used, which takes a variable length input and produces a 32-byte output, and function G, which takes one input and produces two 32-byte outputs, and extendable output function. This is the actually version of Shake. So that this takes 32-byte input and produces a 64 into eta bytes. And central binomial distribution, it functions in Kyber to produce the secret key S and the error noise vector E in the form of the polynomials. And entity number theoretic transform. So here it is basically used for multiplying large rings, large polynomial in the rings. Basically, this Kyber in Kyber, all the polynomials is represented on the ring. So this entity speeds up the multiplication process of the large polynomial, and compression and decompression, this aids in decreasing the overall parameter size, and thus like it is used for to discard certain lower bits from the public key and ciphertext. And encoding decoding, it is used for the byte encode and byte decode algorithms which are employed for serializing and deserializing arrays of integers under modulo M. So this is in Kyber we have PKE, that is public key encryption, which is used as instantiation for KEM. So the under PKE we have key generation, encryption and decryption, and which is instantiated to MLKEM, that is key. There also key generation happens with the input of key generation from the PKE, and encapsulation and decapsulation. So these are the algorithms which are involved in that. And when we go to this Kyber PKE, random input is some random D bit which is of 32-byte array, and output is the encryption key EKPKE, and output is decryption key DKPKE. So as we can see in this, we are generating some 32-bit random byte D, and we are hash of D is done, that is G of D, which generates a public seed row and sigma, which are each 32 bytes, and matrix A is generated from the XOF of row I and J, and then sample entity is done on that to generate a vector A, and this vector A is stored for the later computation purposes, which we do it in the below, where tcap, where we generate a linear equation. Tcap is equal to a cap s cap plus e. So to this for this this one, a cap values of a cap is polynomial values of a cap vector is stored. And we generate a secret message like S of I, which is a vector form, and we we generate E of I again with the same process, S of I and E of I, and then S cap and E cap is generated, and then linear equation A cap into S cap plus E cap is generated. This is nothing but the error polynomial which is added to the linear equation to make a computation even more hard actually. So and then byte encode of TCAP concatenating the public seed row is done to generate the public encryption key, that is EKPKE and DKPKE. So next, if we go for PKE encryption algorithm, this uses the input like encryption key, which is obtained from the PKE key generation. It is given as input to the encryption algorithm. And here input is EKPKE and input message M of byte 32, and again randomness R is another input which is generated by the random bit, and output ciphertext. And here this DUK plus DV, these parameters are taken from the parameter set table. And here again, we actually decode the public key which is generated and generate the TCAP. Then again, we generate the row, and then again, ACAP vector is generated, and sample R and E1 vector and E2 vector is generated. And again, entity of R is done to generate ACAP, RCAP, and U and V are generated. By compressing U and V, we get the ciphertext C1 and C2. So this is this C1 and C2, again it is given to the decryption PKE decryption algorithm, which uses the input decryption key, that is DKPKE, and cipher input is ciphertext C, and output is message M. So here we decrypt the ciphertext messages which is obtained from the PKE encryption algorithm C1 and C2. And here we decompress a bytecode and decompress to produce U and V vectors, and then we obtain a message M. So this the output from the PKE key generation is given as, this is the key generation KEM key generation algorithm. So whatever input output we get it from the PKE key generation, that is given as input to this particular algorithm. So this takes this generates an encapsulation key and a corresponding decapsulation key. So output is encapsulation key and decapsulation key. So it takes the input PKE, EKPKE and DKPKE from the PKE key generation and generates the output EK and DK. And here key encapsulation algorithm, again it takes input message M, and it hashes H of EK and concatenates message M, and again hashes to generate two random, one is the random bit R, and another is the secret key K. And PKE encrypt, this input is instantiated from the PKE encryption algorithm, that is EK, M and R, to generate the ciphertext. And again, shared key is generated with the hash of C and K, and to generate return the shared key and the ciphertext. So in the decryption, what happens is we just start extracting the DK-EK values, whichever we have obtained in the previous module, and through this we get the C dash and K dash. So here we compare the ciphertext with the extracted ciphertext. So if it doesn't match, then we do the implicit rejection, or else the shared secretary key will match here, and K dash will be given to the K. So this is how the algorithm is. It takes the PKE encryption key generation module, it takes Z as input and generates the EK DK, and key Kyber encapsulation, it takes the EK and the message random bytes 32 it takes and generates the ciphertext C and K, and shared secretary K, and here in decapsulation it takes ciphertext C and 1632 bytes of decapsulation key and generates and checks if C is not equal to C dash, it implicitly rejects, and if it matches, then it shares the shared secret key. So for our validation purpose, we need the vendor to provide all the intermediate results of the he is supposed to give the seed, PK, SK, CT, SS, and all the intermediate values of Kyber algorithms, including various sub cryptographic primitives and hash functions. Output of all this he has to submit to the lab. And this shake SHA-312, SHA-3 256 shake, all this will be validated with respect to the SHA validation suit. And TRNG, which the vendor will be using for generating random bits, this has to be validated with the NIST SP 890A. It has to satisfy these standards 890B and 890C. And output of all this polynomial arithmetic functions, encoding, decoding, compression and decompression, all these module functions has to be shared to the lab. And as part of this validation, we are supposed to do a side channel analysis also. So we follow the ISO standard 17825, which is based on the test vector leakage methodology. And this is our lab generated outputs. Above is the request file and down is the response file. So this is how we have captured the data, and still we are in the working mode, and still it is study is going on, and again we are generating the outputs and checking. So it is not finalized. And these are the references. Thank you. Any questions? Questions? Thank you.
Okay, thank you, Madam Jacob, for your good approach about post-quantum cryptography validation.
Thank you. Now I will request Sri K.S. Vatt, Advisor CDAC, to felicitate our sessions here. Sir. So we have our next talk on NIST standardization of post-quantum cryptography. Well, we'll start in 5 minutes. In between, if you have not already taken, take tea and come back. So we'll start with our next invited talk. So the title of the talk is NIST Standardization of Post-Quantum Cryptography and Beyond, Present Challenges and Future. The speaker is Dr. Angsuman Karmakar. He is an assistant professor at IIT Kanpur in the Department of Computer Science and Engineering. His research interest lies mostly on post-quantum cryptography and computation on encrypted data, which are currently shaping the landscape of cryptography and computer security. His work spans a wide spectrum of these fields, such as developing theoretical instruments for efficient scheme design, designing algorithms for efficient implementation, discovering side channel, fault and microarchitectural attacks, and proposing countermeasures. Sir, welcome. So first, I will request Sri Dilip Kumar Burman, sir, Assistant Controller Office of CCA, to felicitate the speaker with a song.
Okay, how to bring this? Is Zoom I have to share? Here? Oh. Share?
Yeah, share. Full screen.
Slideshow?
Yeah. Yeah.
Okay, hi. So thank you for the nice introduction. So today I'm going to talk about post-quantum cryptography, and probably you know that there is a new standardization has just happened 2 weeks back. The new 5th standards have come up, but is it enough? So my talk will broadly cover all those things. And what next? What the next challenges lies in the world of post-quantum cryptography? So I'll not go into very deep technical details, but it's more of an overview. But yeah, feel free to ask me questions after this. So everyone, thank you once again. Good morning and welcome. So let's see. We know that asymmetric or public key cryptography is an indispensable and crucial component of security in our digital ecosystem. So they have lots of applications, from digital currency to digital signature, homomorphic encryption, secure key establishment, and many more. Now, the security depends on the hardness of some computational problems. So the majority of our public infrastructure is based on RSA and elliptic curve cryptography. So basically, their hardness is on integer factorization problem and the elliptic curve discrete logarithm problem. So as I said, these two problems secures our entire spectrum of the digital ecosystem. Okay, so the problem is that given in RSA, so you are given an N and you have to find PQ. Similarly, for discrete logarithm, we are given K and G, you have to find E. Now, these are actually very hard problems to solve. Now, even if we combine all the computers in the world, time to solve just one practical instance is much more than even the age of the universe. Okay, so this is a quantum computer, and this man is Peter Shor. So in 1994, he discovered an algorithm, which is a quantum algorithm, which can factorize a number n into its prime factors, and it runs in quantum polynomial time. Soon after this problem was discovered, there was another algorithm by John Proust and Christoph Zalkan, Proust-Zalka's algorithm, which can even solve this ECDLP problem. So basically, with these two problems, this is catastrophical for our current public key infrastructure. Okay, so as these two problems can break our current public key infrastructure, we need quantum hard problems to build our next generation of public key cryptography. Now, a very watershed or landmark event that happened in the world of public key cryptography is this NIST standardization for public key cryptographic schemes. So, a brief chronology. So, they first announced the plans for standardization in 2016. And on 22, after many rounds of 3-4 rounds of evaluation, they published 3 schemes which are going to be standardized. There's a Kyber, Dilithium, Falcon, and Sphinx. And just 2 weeks back, they have everything published as a FIPS, Federal Information Processing Standard. Now, we also designed one scheme, and this was actually one of the 4 finalist schemes. It's called Saber, which was one of the finalist schemes in this process. Okay, so NIST standardization is not only standardization. So there are many standardizations. So for example, Australia, EU, France, Japan, South Korea. South Korea is not even talking about NIST standards. So see, they are almost following the NIST standards, but South Korea is currently running their own standardization. It's called Korean PQC standardization. So this is the NIST standardization. So we have now PQC standards, and we ultimately go here, this widespread deployment. But to go there, we have to solve many more problems. So for example, we have to do efficient implementation on different platforms. The biggest threat is physical attack analysis and their countermeasures, masking, formal verification, and much more threat analysis, so that we have enough confidence to put them in the public domain, right? Okay, so I'll talk about very few challenges. So one biggest challenge is lightweight PQC. So this is a learning with errors problem. Probably this is the most dominant or very popular scheme, hard problem to design post-quantum cryptography. So on the left-hand side, so the items in the red are the public values, and the green are the secret values. So these are basically kind of a system of approximate equations. The goal is that given A and B, you have to find either S or E, both are equivalent. Now you can see that if E was not here, it is very easy to find. You just do some Gaussian elimination and it will give you S. But unfortunately for the, fortunately or unfortunately, whatever you say, that if you add E, this becomes very hard. And Regeb's original proposal actually described this, they proved it, that this is a quantum hard problem. So, but the problem here is, see, if we sample all of these things from randomly, we have to perform this matrix vector multiplication, which is of order of n square or n cube algorithm. These are extremely slow. These are extremely slow, and the sizes is quite large. So in 2012, but there is a very popular scheme based on this problem. It's called FIDO, which is in use in many products. Okay. So yeah, now we actually have come into module learning with errors. What do we do? And Kyber, Dilithium are all based on these things. So here you see, earlier we were just sampling each number, but now we do not go for a matrix of numbers, but we matrix of polynomials. So each of them are generated, are polynomials, and these are all ideal vectors. So here on the left, instead of this large A, we get a polynomial matrix. The secret is also a polynomial vector, error is also a polynomial vector, and the output is also a polynomial vector. Now, this is actually a trade-off between a standard and ring lattices. So ring lattice is also, it is very well known. New Hope, one is a very famous algorithm dependent on this. But the problem is that people do not are satisfied by the security reductions of ring learning with errors, because whole polynomial is generated by whole matrix is generated by one single polynomial. And people say there are lots of structures, it might be broken. There's a huge rift between the researchers whether it is at all secure or not. So there is a trade-off, this module learnings. So it is not fully ring, not fully standard, something in between. What is the advantage? Advantage is, see, since each of these polynomial multiplication, you can do it using very fast algorithms like NDT, which runs in order n log n, right? So it is, and also there are much more elements like standard lattices. So it is believed to be more secure. Actually, there are reductions which shows it much more secure, like standard lattices. So yeah, the thing is now here, if we consider there are L corps L polynomials here. Right now, there is no attack that can take advantage of this structure. So we assume that if L is this size of this matrix, L cross L, and N is the size of these polynomials, If L cross N becomes some, the rank of the standard lattices, all of their security is same. Now, examples are Kyber, dilithium, saber. It's not moving. Okay, so the thing is, what we have to do is for module space exploration. So why it is important? Let's see. So here is a matrix. Now you can you have to do this polynomial multiplication. So you can put, let's say, n processors here, L square processors. Since all of these multiplications are independent, you can instantiate many such parallel multipliers. Of course, it is very good for very high performance devices. So the latency is very low, but it also requires lots of area, energy, right? Now another scenario is you do not keep so much multipliers, but only one multiplier. The thing is, it is very slow. The latency is very high, but also the power consumption is also very low. So using module lattices, you can move to very high power or very low power designs. It is not possible with ring LWE or the standard lattices. Now, so this is one scenario which is very useful. So this is a very simple generic architecture of an IoT gateway. Since probably you know that IoT devices usually do not connect to the public internet directly. They used to go through a gateway server. So gateway server is quite large. It is stored, it is powered with very high power electricity lines and everything. So here and also remember that these gateway servers, I mean, these IoT devices may be in 1 day or 1 week or in 1 month may connect to the gateway servers just to send their data. But these gateway servers, they serve lots of these IoT devices at a time. So for our gateway server, the throughput is much more important. But for these IoT devices, low power and low energy is very important. So what we can do, so using the same one single algorithm, one single scheme, module lattices, you can instantiate on the left side as a very low power implementation. But on the right hand side, because these are very powerful devices, you need high throughput. You can instantiate a L square multipliers, and instantly you have a very high throughput device. So with module space exploration, we can do this. Now the problem is, so see, I mean, I told you that even in the lowest case where you have only one multiplier, for Kyber, dilithium, saber, you must have a 256 cross 256 multiplier. You cannot go beyond that. This is the limit. So see, this is the see, this is the some recent results. So this is our work. So you see, these chips are not low power. So this is 140 milliwatt, and usually for IoT devices we consider around 1 to 10 milliwatt. And these results are not even considering this KCHAC code. So even if you put the KCHAC code here, the problem is that these are not at all suitable for these IoT devices, right? And also the area is quite high. I mean, you cannot put them in IoT device or small devices. So yes, so even for the standards, there's one single multiplier is very expensive for small devices. So we have to explore other module lattices with different combinations of N prime and L. So what do I mean by that? So as I told you that since if N prime and L, if their multiplication is constant, the security stays same. So we can vary N prime and L, but we can still keep the same security. So this is a module space. So let's, in the standard lattice, what I told you, standard lattice, each number you can consider as a polynomial of degree 1. So in standard lattice, N prime is equal to 1 and L is equal to 768. Example is FIDO. On the other band, on the other end of the spectrum, you have a fully one polynomial, whereas N prime is 768 and L is equal to 1, which is called ring and ideal lattices. So examples are New Hope, Lizard. In the middle, you have some combination where N prime is 256 and L is equal to 3. For example, dilithium, saber, everything. But this is the module space. But what about others, right? We can have many more such combinations. So for example, think about this. If we go for something like N prime is equal to 64, I'm talking about this one multiplier. One multiplier becomes already very small. So think about this IoT scenario I told you. You can have a very teeny tiny multiplier inside the IoT, which is very low power and still give the same security as your standards. So we have to do, for lightweight, one solution is to do this module space exploration. Okay. Now, this is the woe of our random numbers. So when we design schemes as a cryptographers probably know, we often assume that random numbers comes almost for free. We focus on much more to think about your ECDSA algorithms, your RSA algorithms. How many times have you thought where this random number comes from? For them, it's fine because there we do not need so much random numbers, right? So we assume that they come for free and we just focus on improving this point multiplication, polynomial multiplication or scalar multiplication. Unfortunately, in normal lattice-based systems, even in the standards, we use SEC128 or SHA-3 as a random number generator. So this is usually how it is generated. So this is a large matrix where each of them can be a polynomial. We start with a random seed, we put it into SEC128 and you see, we need lots of random numbers, 3.8 kilobytes of random numbers. It's already huge. And we have worked to improve in the main operation, which is polynomial multiplication. Unfortunately, we have improved it so much, the polynomial multiplication. Now, the random number generation, which is kind of an auxiliary component, it takes around 70% of the time in some cases, and 50% of area. So it already is very huge. Okay. But fortunately, we have something, it's called ASCON. ASCON is also a niche standard, which is a very lightweight design. So one possible solution is to remove the SHA, use the ASCON. Okay, so we have done some work in this case. So recently we designed schemes called Rudraksh. So it's a kind of very Kyber-esque design. I mean, very similar to Kyber, but we did this module space exploration, and we found that for n prime is equal to 64, it gives almost the same security. We also used ASCON as a random number generator, and it actually has the initial results show that it is ultra lightweight design. So it is available online. The very good thing is this is 3 times smaller than the state-of-the-art smallest design of Kyber. So we are doing ASIC fabrication. So also the similar thing we did earlier is called Espada, which is based on again same ideas, but it's based much more based on module learning with rounding, not errors. So I just want to mention that this Espada, that scheme we designed, this module space exploration, I told you about this Korean PQC, and there is a scheme called SMOG. So basically this Espada is, I mean, SMOG is heavily inspired by Espada, and it is now a second round candidate in KPQC. Okay, so now more deployment issues. So the large signature issues. So PQC is very large. So think about this. These are the ECDSA signature size, which is in a couple of bytes or maybe a few hundred bytes. Now this is the size of dilithium. This is a huge size. Almost in the lowest setting, you get only 2.5 kilobytes of signatures. So, and this incurs a lot of overhead in time and space for TLS. That's why people are coming with new revolutionary ideas like KEM TLS. We do not use the certificates at all. We do everything using KEM because of these things. Think about in a CA setting where you have this root certificate, lots of intermediate certificates, and then the end certificate. How big will be your signature if all of them becomes 3.3 kilobyte? Think about this transmission overhead. Think about this computation overhead. It's huge. Right, and this is the reason. I mean, there are many problems. I mean, I have seen papers. People are working to remove these problems for these different protocols, and for the same reason, the NIST has initiated a new call where they have particularly focused that we have to design new signatures with smaller signature and very fast verification time, which unfortunately none of our current standards satisfy. Clear? Then migration issues. How do we migration? How do we do migrate to PQC? All of our infrastructure is based on classical. So there are many legacy systems where you cannot put PQC anymore. There are different organizations. They are not maybe they adapt to new schemes in a different pace. Also, it's already. I mean, there are many IoT devices which you cannot just collect and put a new device and redeploy. So the only solution at this moment is designing hybrid schemes. So one example is okay, so hybrid schemes basically works with both classical and PQC, but it's not just simply you just merge together and everything will work. I mean, there will be many attacks. So I have given one very simple hybrid signature setting. So what you do in this case, you just do a first signature using this classical PQC, and then you do another signature with the message and the classical signature, and then sign this with the post quantum. Then the final signature becomes a concatenation of those two signatures. Now, if someone doesn't support PQC, they will only verify this first signature. If someone supports, they will verify both of these signatures. Although a thorough security analysis is, this is still a burgeoning field, it's in the very nascent stage, but a thorough analysis is required. Okay, now agility issues. What is agility? So this is our public key, let's say we have designed a crypto processor. So I just told about the hybrid system. So this crypto processor must also work this with the classical cryptography, the standard PQC schemes, and then strong backup schemes. Why do I mean this? So because breakthroughs always happen in cryptanalysis. If you think about the lattices, right, the RLW or LW problem, these are barely 20 years old. I mean, in cryptographical terms, they are quite immature. So for example, these were two very popular schemes, Rainbow and SIDH, and they were broken completely. They were the finalists. So after 2-3 rounds of the evaluation, they become finalists, and then they got broken. So it might quite happen that there is a breakthrough in cryptanalysis of lattice schemes, and our current standard schemes, their security is reduced. So in this case, what we have to do, we have to keep some backup schemes. So NIST also mentioned that this is important, and that's why they have put Sphinx and McElis also as a backup schemes, because these Sphinx and McElis are 50-60 years old schemes, and we are very confident about their security. So this agile crypto processor, we have to put new crypto processors which are very agile, which can not only do dilithium, Kyber, but many things. Okay, yeah. So just this hybrid processor, and then of course this physical attacks countermeasures. So this is one of the most potent threat for deploying this any cryptographic schemes. Now your scheme can be very secure mathematically, but unfortunately when you run it on a processor or your microcontrollers or wherever, it is possible that I do something on this, these things leak a lot of information about your secrets. So this can be passive attacks like power side channel timing, electromagnetic radiation, or it can be active attacks like voltage glitch, row hammer attacks, cache attacks, electromagnetic attacks, etc. Okay, so we did one work. So this is based on, because we attacked this core component of any lattice-based scheme. So this, every lattice-based schemes, they use polynomial multiplication. So we did this correlation power analysis attack, and we exploited this narrow distribution of secret values. And our attack worked on 3 out of 4 finalist schemes. That means Kyber, Saber, and N-True. And it worked on all of these different multiplication methods, and we were able to recover all the secret values. So this is a published work. So we will able to recover all the secret keys within an hour in the online phase. Okay, so protection schemes, of course, we have to work on lots of masking schemes. So how the masking schemes work. So you have this input and output. This is your secret. If I do side channel attack, I get information about S. So in masking, you split the secret in 2 parts and then repeat the same operations. And then somehow at the end, you combine. Now the goal is that even if an attacker is watching one part of this algorithm, he or she doesn't know the other part. So your secret stays safe. So these are the basic concept of masking schemes. But the problem is that masking, although provides this provable security, see, there are some state-of-the-art implementations. You see, for the third order masking, the Kyber's overhead is almost 30 times. So it's huge overhead, right? Although it's secure. So now think about these IoT devices. They are not even applicable for IoT devices. That's why we have to find some new methods like shuffling, chip level countermeasures for IoT devices or low power devices, right? Okay, so then then we took it one step forward. I mean, there's a new type of attack comes in. It's called cross attack. So why this is important? I told you about this side channel attack protection in masking, right? You have developed lots of good masking schemes, and now you have put it into public level. Now you cannot restrict the attacker. They see, this is my side channel protected scheme. You cannot do any other attack on this. Attacker is free to choose any type of attack. Your scheme may be side channel protected, but I can do fault attacks on that. So this is the idea of this work. So this was a masked implementation. SC attack is not possible. It was proven. But then we saw that we can do, because to put this masking, you have to introduce many new components. And we can actually put faults there, and it gives us a much more advantage than normal fault attacks. So this is again a published work. It is one of the top flagship conference for this type of work. Okay, then I think I'm running out of time, so I'll quickly finish. Then the problem of indigenization. So this is a very basic very basic life cycle of a cryptography scheme. We start with hard mathematical problems, then we design, we propose parameters, then we do proof of concept implementations, we do physical attack, then we do some optimized implementations, we put it into protocols because these are primitives, and then we deploy in the real world. So for indigenous design, we have to do, so we shouldn't really outsource any of these parts to, at least for the national security or for very critical components, we shouldn't give it to third parties. The thing is that, we didn't have any standard documents, standardization. It's fine, we do, but after this, let's say we have designed and did everything till here, but we didn't get to synthesize our chip to some company. The thing is, it is very easy to put some backdoors there, and then everything is, there is no point in doing everything because your scheme is ultimately weak. So this is the point of, we have to focus on covering all these parts indigenously. Since only we can move into a proper PQC, quantum secure world. Now the good thing is, right now our group, and there are many other groups, few other groups in India, which with combined expertise, we can almost cover the entire spectrum. So I have just given some of my works. So we have designed lots of schemes, which are some of them are state of the art. So this Saber, which was one of the part of the finalist, then this Rudraksh, which is a lightweight design. This PQ signature FIDO we have designed based on multivariate. Right now it has the lowest signature of only 96 bytes among all the post-quantum signatures. Then we did lots of software implementations, many fault attack and side channel attacks. Some micro-architectural attacks. This is one of the first of its kind, doing row hammer attacks on Kyber. Also, we did lots of countermeasures for all those attacks, and then of course, then we did some ASIC implementations, which is, as I showed you in one of my earlier slide, that one of the lowest power and lowest area design of PQC currently in the market. Okay, so I'm done. I will be happy to answer your questions.
Good talk in a very short span and a lot of work.
Yes.
The balance between lightweight to all the heavyweight,
yes,
which you showed, is it a matter of choice of this, at least for crystals?
Sorry, I'm not. Yeah, please.
Is it a matter of choice between the 3 parameters, ring size, the modular, let's call it the finite field size, exactly, and the module matrix size?
Exactly.
Is it the question of that? In which case, my just last question, have people studied the variation of these with the lattice hard problems, their dimensions and so on?
Exactly. So that's a very good question. Thank you for asking this. So yes, first of all, of course, it is kind of, I would like to call it as an optimization problem. Right? You can, so for example, I can give you, so you can reduce the queue. The problem is that if you reduce the queue, then it becomes very prone to failures, because lattices are not 100%. These are actually error-prone solutions. We want to keep this less than 2 to the power minus 128, the failure probability. It is not like 100% perfect solutions like RSA or Diffie-Hellman, right? So it is kind of an optimization problem. We have to choose many different parameters and then, tweak something there and tweak something here. Basically a search problem. So, I really cannot, I'll be happy if you can read the paper and let me know. So there are many things we have to optimize. It's a multidimensional optimization problem, I would like to say. So then we did a huge level of search. It's not like just I run a Python program and I'll give, it give me the parameters. So we have to do lots of changes in between and then see how the results come up. And then we got a satisfactory result and then we put it in. Your second question is, see, these are all modules. So the good thing about modules is modules give a very uniform view of these whole lattices. The spectrum I showed you, see the standard lattice and ring LW lattice, all can be thought of as a different dimensions of lattice. So as long as we stay in the module space, there is reduction from ring SIS to module SIS. So as long as you stay in this module space, we are fine with this security problems. So does this answer your question or?
That's okay. Just an extension, small. That's fine. Module space. Now, in general, learning with errors, this even some kinds of a code error decoding problems, and then the lattice problems, they're all similar. Okay.
Exactly.
So it's worthwhile probably to invest a lot of.
Exactly. No. In the paper we have did a thorough evaluation of everything. So all the different types of attacks have been considered, and then we designed we proposed the parameters. Of course, I know this must be done. Yes, we have done it. Thanks. Thank you for the question. Yes.
Sir, can you tell us like how difficult it is to do side channel analysis on the quantum algorithms?
Well, this is very much matter of perspective. As I told you, this fault fault attack on side channel, it was very complex attack. So we had help from Professor Devdeep Mukhopadhyay's SEAL lab. There are like the CPI attack. This was, I would say, a bit easier than this attack. So it all depends on what type of adversary you are assuming, what is your setup and everything. So unfortunately, I cannot comment on how easy it is to do attack, right? Yes.
No standard formulation has been done.
No,
we have to identify which module has to have more possibility of finding the side channel attack, right? So then how do you execute that side channel attack process in your?
So I don't know, how do we execute? Every
module has some specifications, right? So you have to focus on the module where the side channel attacks are possible.
Okay.
So how did you define? Because as of now in this, the standardized has come out, but verification has not come out.
So NIST doesn't standardize any fault attacks. Okay, it will only or any type of attack. It will only standardize the scheme. So think about the AES, right? People are still finding new dimensions, new type of attacks on AES. So this field keeps progressing. So when we see that okay, what are the existing attacks, and if we can improve this, if we can change this parameter, you can change this setting, if we can improve these attacks further.
Keep improvising these schemes. That's a good design. So when
I said improving these new attacks. I mean, you cannot say that after this time there will be no different fault attack or side channel attacks possible on these schemes. So as I gave you this example, people are still finding AES was how much 25 years back. Still there are new attacks on AES, right? So,
but comparing to this post-quantum algorithm, because as compared to many of the checkpoints, what the NIST has been done, still the fault attacks, the side channel attacks, the possibility as well as you have been coming out with your lightweight cryptography, Rudraksh, for the replacement of Kyber.
Okay.
So in that possibility, you have overcome that side channel attack.
Exactly. So while designing, because we have designed this after, while NIST is proposing new standards. So we have already in the paper, we have mentioned that how it can be. So we there's a concept it's called masking friendly designs, or so we already have put some design strategies here, which will make it little less prone to fault or side channel attacks. Also, these masking schemes and any other countermeasures you are developing for Kyber, those can be applied to our designs also. Because see, I am talking about module space, right? So we are just reducing the polynomials and increasing the matrix size. So those countermeasures which you are applying for Kyber, it can also be applied for our schemes. Also, the schemes which the attacks which are applicable to Kyber is also can be applied to our schemes. So
whether your scheme overcome that the drawbacks of the Kyber.
So we can only make it less prone to attack. But nobody can say that our scheme from design is prone to these attacks. It's not possible. Yes.
So while optimizing the parameters or dimensions, how you will ensure that this will remain FIPS or some recent?
Okay, so this will not go into FIPS, but I would also like to say that please, I have encountered this question many times. FIPS doesn't mean the end of innovation in the field of lattice-based cryptography. As an example, there was FIPS 203 for elliptic curves, right? After that, there were 5 more standards. Right. Fine. So it is not like that since a FIPS has published, we should stop now. We should keep innovating. And there is actually a lot of buzz in designing lightweight for post-quantum cryptography, because as I told you, NIST itself has initiated a new scheme, new process to standardize more signature schemes. So it is not like that FIPS 203, 204 and 205 have been developed. We should stop here. No, we have, and there are. So this KPQC schemes, if you see the KPQC schemes, there are more designs coming up, and even in the ePrint, lots of new designs coming up. So in 1 week, I have seen a very efficient intro-based design in ePrint. So, yes.
But at the same time, this is that if it is not standardized, it means it is not secure. Actually, this is what, or there is no security. Actually,
no,
there is statement actually.
So this is in the design, I wrote one word that I love to call it. It's called Kyber-esque designs. So Kyber-like design, right? So we have taken into, we can show that if our scheme is vulnerable, Kyber can be also vulnerable. So our scheme is almost as same level as security as Kyber. So now if you are a designer, if you are a new, let's say you are implementing, you want to do IoT implementation of Kyber, you cannot do it. I just showed you. Then you have the option to do these things, right? And there will be maybe, so we had AES, but we still did a lightweight standardization with ASCON. So it is a possibility that in the future there will be a lightweight PQC competition, and there we will submit. So once NIST announces a new standardization protocol, you cannot start working then and submit something, right? You have to be prepared from much before. So I can see it that way. Okay, yes.
So I have one quick question. That is, first of all, thank you, Angshuman, for this nice talk. So when you talk about like lightweight PQC, right?
Exactly.
So you have also considered, I believe, like other problems like LWR based and also
exactly.
code based, right?
Exactly.
So do you think that, like there is an opportunity to look into those hard problems in the context of, like getting maybe, designs which are based on 0 and 1 or binary,
exactly.
decompositions?
That's a very good question. Yes, exactly. So we are looking it into different different lattice combinations and also other schemes. So the one I think it was in the design is called VIDO. VIDO is a multivariate based design, and it has only 96 bytes of signature, which is smallest as far as I know. Right. So why I showed you this Rudraksh design, because this is very much similar to Kyber, and just as I discussed that it is much more easy to argue that still it is secure. So yes, we definitely has to look for. So I just want to again tell that even in this new call for signatures, they have specifically mentioned that they do not want any more lattice-based designs. They will focus on other designs more. So of course, this is we have to look into others, and I personally feel that because of this so much popularity of LWE, the other designs, this code-based, multivariate-based, and these things are quite neglected. So it is right time to look into those things.
Yeah, when you look at LWE, right? Usually there is an error involved, right? But when you look at the counterpart like LWR,
exactly.
Right, it is more deterministic. Right?
Exactly.
So that is an interesting, choice in the context of things like fault and things.
Exactly. So we already designed one LWR with integral 64, which I told you. So this is actually quite. This was acknowledged by the designers. This is very much influenced the SMOG scheme, which is currently in the second round of Korean PQC. So yeah, we already have done some work there. Yeah, that's a good. Of course, this is LWR is always very attractive scheme to design. It has much more. So apart from LWE, it is very, very, very friendly for masking designs. Okay, any questions? Okay, thank you, everybody.
Can you please wait?
Oh, okay, wait.
Thank you so much, sir, for your insights. I want to request Shri Anup Kumar Pandey, Scientist E, CDAC Bangalore, to felicitate Sir with memento. For the third paper presentation session, I would like to request Shri Dilip Kumar Varman, Assistant Controller CCA, to be our session chair. And I would like to request Professor C. Murli, Academic Expert, Distinguished Fellow, IEEE India, to felicitate Sir with a shawl.
So in this session, we have three papers. The first paper is by Ms. Geeta, experimenting integration of custom ECDSA algorithm in OpenSSL. Ms. Geeta, please.
So good afternoon to all present here. So I'm here to present a paper which is titled Experimenting Integration of Custom Implementation of ECDSA Algorithm in OpenSSL, which is co-authored by Ms. Akila from SET Chennai, and it is mentored as a part of UBS project by Dr. T.R. Reshmi, scientist and a principal investigator for UBF at SET Chennai. It's not working actually. Yeah. So the overview of presentation goes like this. So introduction to the OpenSSL, an open source software library, crypto library, and review on attacks that has happened inside the OpenSSL crypto implementation. So the methodology by which we can add a custom implementations of any asymmetric or symmetric algorithms into OpenSSL. So which prescribes three methodologies through OpenSSL libraries, engines, and service providers. Recommendations for custom crypto additions based upon the applications, followed by conclusions and references that has been used for this presentation. So we would like to start with an introduction of an OpenSSL. So the OpenSSL is one of the most widely used cryptographic library for establishing secure communication over a TLS protocol. Almost all of the TLS communications, HTTP and web servers today in an internet world use an OpenSSL. So an attacking OpenSSL cryptographic implementation, of course, may take the web server or an internet environment by storm. So it is also, the OpenSSL also plays a vital or key role through its cryptographic interface for secure key storage solutions like HSMs, facilitating the cryptographic operations inside those storage devices like tokens, hardware security modules, or smart cards, etc. In this regard, there is a growing need to customize the OpenSSL cryptographic modules for two main reasons that we have identified. One is to mitigate the known vulnerabilities that exist in OpenSSL implementation. By the next slide, we will be showcasing the prominent attacks that has happened on the OpenSSL crypto implementation. The second is to integrate the custom cryptographic solutions into applications like blockchain, where we have our own ECDSA implementations that will generate the key pairs, but yet the X.509 certificate and other the attribute-based certificates CSR, yet we can able to use the OpenSSL implementations. So in this regard, this article explores the method for adding custom cryptographic implementations into OpenSSL library, and also discusses the advantages and the disadvantages, the overhead that we are going to encounter by doing this. So this presents the prominent literature review on attacks that has happened on an OpenSSL crypto implementations. We have given only the 4 attacks, each for one algorithm, whether it is maybe a symmetric or an asymmetric algorithm. So first, it is a cold boot attack that happened on an AES 128 implementation of an OpenSSL in OpenSSL version 1.1. The nature of an attack, so by AES, there was multiple round operations. Of course, we know that. And to just reduce the overhead and improve the efficiency, it is a model to just pre-compute the round keys for an AES operation, store it in a consecutive address space of the memory, and then you can able to use it for your round level operations. So the nature of an attack is to redrive the pre-computed AES round keys from the memory dumps. And it is successful in redriving 11 disordered 128-bit AES round keys in an OpenSSL version 1.1, and 60% has been assembled to form a proper round keys. The second is an RSA and catch bleed attack that happened on an RSA implementation, on a 1024-bit RSA implementation of OpenSSL version 1.0.2f. So based upon the timing excess of a level 1 catch, that is a so RSA as a modular exponentiation operation. The exponentiation is of course a high power consuming operation. So based upon the level 1 catch access, it retrieves about 60% of a 1024-bit key in an RSA. And the second is an SCPD attack, that is singular curve point decompression attack that happened on an ECDSA. So attempt to know the SCP curve point, base point variant before a scalar multiplication, thus leaking a secret value. So fetches a private key from 140 signatures. So it happened in a version OpenSSL 1.1. And the fault injection attack that happened, is it a basic side channel attack that happens in ECDSA implementation, retrieves the secret key from the minimum number of signature, ECDSA signature, that is 4 signatures. That has also happened in a OpenSSL version 1.1. And of course, there are known vulnerabilities like heartbeat vulnerability that exist in an OpenSSL implementation. Yet it is one of the most widely used software library. It is an open source software library, so we have freedom to customize the open source software library based upon our need. So that is our point of discussion. So this is an architecture, OpenSSL inspired architecture from an OpenSSL documentation. So we just identify 3 places where we can add a custom crypto implementation into an OpenSSL. So one is the common services or the lib crypto modules, which is again the regular crypto operations or crypto modules inside an OpenSSL will be hosted in the lib crypto module under a common services section. The second one is the legacy APIs, an application programming interface, which normal public key crypto standards, PKIA standards will be using to interface their engines into the OpenSSL. And the third is, which is supported by OpenSSL version 3 and above, which is a third-party service provider API, which is hosted for vendor-based crypto algorithms. Like OQ is one of the most commonly used post-quantum service provider that uses a third-party service provider for an OpenSSL implementation. So in this regard, we have summarized 3 methodologies by which a crypto implementation can be added into an OpenSSL. So first one is addition of new crypto algorithm into lib crypto module of an OpenSSL, creating a new engine which is similar to a PKCS 11 engine for an OpenSSL with custom crypto implementations, defining a service provider library with a set of custom implementation, and interfacing the library, third-party library with an OpenSSL. So we here discuss the steps with which we can able to accommodate or incorporate these custom crypto implementations by these frameworks. So the first one is through OpenSSL libraries. So the addition of custom ECDSA implementation, which is written in a C language, into the inbuilt crypto folder of an OpenSSL. So there is a language dependency. So because the OpenSSL crypto modules or crypto implementations comes with a structure which is called as an EVP, which is called as an envelope structure. So the structure must be strictly followed in order to incorporate your custom crypto implementations. So the source files, which is written in a C language, must be added into the crypto folder. So you have to follow the EVP interface for the integration. That is, your algorithm and the code must be in a structure of an EVP, and you have to create an object identifier, the crypto module object identifiers. You have to map all the utilities like error collection, error creation, error collection, etc. For as asymmetric algorithm, since it is also works on a TLS layer, so you have to configure a TLS settings and you have to go for a build info. The next is through an OpenSSL engine. OpenSSL engine is a modular framework that enables the integration of various custom crypto implementations for hardware security modules or an alternative software algorithms to an OpenSSL library. So the public key crypto standard, crypto key version 11 is one of the mostly used OpenSSL engine for module integration of secure key storage options with an OpenSSL. So the implementation of custom ECDSA based engine in OpenSSL requires an engine structure that has been defined as the right hand part of a slide. So this is a structure with which you have to test your define your engine, test your implementation, compile it and load it, and you can able to interface it or call it from an OpenSSL. And the last part is a service provided to an OpenSSL. So as we already mentioned, the OpenSSL version 3 and higher versions host the provider API, that is a third-party provider API, to which a custom cryptographic implementations can be incorporated into an OpenSSL. So the detailed workflow or a pseudocode for this implementation has been submitted as an annexure or supplementary material along with our proceedings. So the provider holds a set of cryptographic implementation, and it has been initialized by a provider.c file to the OpenSSL. So the custom algorithm will be implemented and will be attached as a calls to the providers, and a make file will be returned. A make file will contain information, the necessary information about the object identifier of an algorithm, the structure of the key, the time taken for the key generation, signing and verification phases, and of course the error collection, error codes. Everything will be written, and the make file will be called by means of the test application. So you can able to see when you are able to interface an OQS service provider to the OpenSSL, it comes with the OQS crypto implementations, and OQS will supply you the PQC implementation along with the structure of the key, the size, and of course the time taken to generate the key, and the average time and the error code. Everything will be supplied by the OQS third-party service provider. The OpenSSL command line will directly call as it is an implementation of an crypto implementation through the service provider algorithms. So these are the three methods with which you can able to add a custom crypto implementation into an OpenSSL. But we have some, as we have tested all the three implementations, and we are going with the adding a custom crypto implementation inside the libcrypto module of an OpenSSL for our application. We have some recommendations in this regard. So the first one is the engine or a service provider may be lightweight, may be easy to host it. While using a separate engines or a service provider with OpenSSL will reduce your overhead. But it is important to know that your crypto implementation will no more be secure. It will reside outside your OpenSSL software implementation. So the external placement of a crypto modules could introduce security vulnerabilities, making them more susceptible to attacks. And some applications like hardware security modules, which interact with OpenSSL through built-in interfaces like PKCS 11, may not be aware of an additional external interfaces or engines that is hosted inside an OpenSSL. So this lack of awareness for HSMs or smart cards or any other storage options may create a compatibility issues and reduce the security. So in accordance with the specific environments, the engine and service provider approach are recommended primarily for environments where OpenSSL crypto implementations can operate independently without requiring a direct application interface. But with this, for our implementation, so we are hosting a CA for a blockchain, and with the secure key storage management system for a CA is accommodated by means of an SSM or a HSM. We have a custom implementation of an ECDSA inside our CA. So we are already a PKCS 11 interface has been enabled for a HSM or an SSM module. So we just avoided an option of promoting one more engine above a PKCS 11 or below the PKCS 11 engine, and we don't want a third party provider interface, since it may again overload your certificate authority. So we thought of we could directly implement or add a custom implementation of ECDSA inside a libcrypto module of OpenSSL. So the article highlights the need for custom cryptographic implementation in applications such as permissioned blockchain and hardware security modules. Embedding a custom cryptographic library directly into OpenSSL is identified as a practical solution for these types of applications. So OpenSSL version 1 supports the integration of separate cryptographic modules into the libcrypto module, allowing significant module modifications into the EVP structures for symmetric algorithms and OSSL structure for asymmetric algorithms. The method, while potentially increase code overhead, enables the addition of cryptographic modules that meets the FIPS standards. It also addresses traditional security vulnerabilities present in other approaches and offers the improved timing efficiency. The choice of integration and the OpenSSL version should be guided by specific needs of an application, balancing security, performance, and feasibility for your application. So these are the references that has been used in this context, and that's all. Thank you. Queries?
And person will take maximum 2 questions. Any questions?
Sir? So it is P256, sir. Prime curve 256.
Any other question?
Thank you.
Next paper is from Mr. Mohit Raspurohit Patil. So Mohit Raspurohit will be presenting the paper. Advanced QKD protocols and practical challenges. Mr. Mohit, please. Is here? Not here? Okay. So I suppose he is not here. Okay. Can you go to the next paper then?
Yeah, we can go to the next paper. Maybe not.
Okay. We'll consider the next paper from Nidhi Bhatt. The comparative analysis of hybrid crypto systems for secure image encryption. From Nidhi.
Yes, sir. Good afternoon. I will be presenting online.
You can share your screen, ma'am.
It's not allowing me to share actually. Yeah, now it is. Yes. Yes. All right. So, good afternoon, everyone. This is Nidhi, doing BTech CSE from Indira Gandhi Delhi Technical University for Women, and I will be presenting my paper, Comparative Analysis of Hybrid Crypto Systems for Secure Image Encryption. Introduction. Safeguarding sensitive images is vital, especially within the PKI systems. Satellite images are more complex and cover larger areas, requiring more advanced processing compared to normal images. Satellite image encryption is crucial to protect the sensitive data from manipulation. Traditional methods such as DES and triple DES are not suited for images due to their large size. So this study compares two hybrid crypto system for satellite image encryption, AES-GCM and Chacha-Poly, and both systems use ECDSA for key exchange and respective algorithms for bulk encryptions similar to TLS 1.3. So they are evaluated using metrics MAC, PSNR, SSIM, entropy, total encryption, decryption process time, NPCR, USCI, correlation coefficients, and bit error rate, BR. So this slide presents the literature review in the context of image encryption. So as we can see, so there has been very little work presented in satellite image encryption, and moreover, the direct comparison of AES-GCM with Chacha-Poly with ECDS key exchange in the context of image encryption has not been presented before. Research methodology. So this experiment is done using Python in a cloud-based Kaggle CPU environment, which provides a 4-core Intel Xeon processor with 30 GB of RAM. So the key step involved are as follows. ECDS key generation using P256, shared secret computation via ECDS algorithm, key derivation using HKDF, image database. So 10 satellite images from deep low bland cover dataset was used for testing. And for each image, the following steps are performed: encryption and decryption, matrix calculation, and visualize encryption strength and store results. And then finally, read and display results for all images and generated time comparison plot, as shown in the figure. So this is how the experiment was done, the implementation. So for key exchange, keys were generated using ECDH, and then exchange the public keys, compute shared secret, use HKDF to derive the final symmetric key. For ASGCM, SHA 384 was used, and for Chacha Poly, SHA 256 was used. For the encryption process, read and flatten the image data, generate 12-byte nonce using os.urandom. So this is a Python function. I have not used this sequence number here to generate the nonce. Initialize with 32-byte shared key, encrypt data with associated data for integrity, then reshape the encrypted data to original image dimensions, then record the decryption time. Similar process for decryption, receive encrypted data, nonce and image shape, initialize with the same shared key, verify authentication tag if valid, decrypt data, if not, then the verification phase, then halt. So this is how the proposed implementation compares with TLS 1.3. Similarities, ECDH key exchange is there, cipher suits, implements ASGCM and Chacha Poly. Key derivation uses HKDF, nonce generation, 12-byte nonsense. Authenticated encryption employs AEAD. Hash functions uses SHA 384 and SHA 256. These similarities are there, so there is no certificate verification. Uses fixed key pairs instead of generating new ephemeral keys for each image. So there is this specific use case. So it's used for image encryption rather than general purpose communication. Simplified nonce handling is there. So this does not include a full network stack integration or practical demonstration of HTTPS SSL. So the focus is on the cryptographic operations. Now to the results and discussion. So both the systems show similar security performance. And the comparison is based on the average of all the metrics calculated across the set of images used for testing. So AES-GCM is faster in all time metrics, as we can see here. Near idle NPCR and UACI values, and both achieve maximum entropy. Average correlation values for the encrypted images is near 0, which is good. So it's continued. So as we can see in the figure 1, for the encrypted image, so there are no visible patterns, and the decrypted image is identical to the original with bit error is 0. So this shows the lossless nature of the process. Onto the next figure. So we can see that AES-GCM is faster than Chacha Poly. So some potential reasons for that can be the hardware acceleration for AES and the specific implementation environment. And decryption is faster than encryption due to additional operations in encryption, as we can see here. So there is nonce generation here. Then continued in correlation analysis. So we can see for the original image, strong patterns are there. And for the encrypted image, so there is this uniform distribution. For the histogram analysis, so we can see for the original image, distant peaks are there, and for the encrypted histogram, near uniform distribution is there across all pixel values. So future work and conclusion. So some future work can be the integration of PQC algorithms, for example, Kyber and dilithium. Testing with diverse image types beyond satellite imagery. Optimization for resource constrained environments in PK environments, for example, in handheld devices. Advanced security analysis using NIST test and gray level co-occurrence matrix analysis, comparative studies with OpenSSL and Wolf SSL TLS 1.3 suites, and full SSL HTTPS protocol stack integration and performance testing against TLS 1.3 latency requirements. So finally, this research can be concluded as follows. Now, the both system exhibit robust security features, and AES GCM outperforms Chacha Poly in speed, approximately 13.33% faster overall. And some practical application of this work can be enhancing the digital image security in PKI systems and potential use in e-governance and IoT applications. These are the references. And thank you. And I thank Mr. Prabhat Kumar, scientist DMET, for his valuable guidance and insights for this paper. Thank you.
Thank you, Nidhi. What a good presentation. So we'll take the third paper by Mohit Raspurohit. It's on advanced QKD protocols and practical challenges. Mr. Mohit. Yeah.
Hello everyone, my name is Mohit Rajpurohit. I'm going to present my work on this advanced QKD protocols and the practical challenges associated with it. I am from CDAC Bangalore and in Quantum Technology Group. Next slide. So this is the outline. First, we'll talk about the motivation to, behind this work, and then we'll see the quantum cryptography, what is quantum cryptography, and advanced QKD protocols like measurement device independent QKD and the twin field QKD. And we'll discuss about this quantum hacking that can be hacked. This quantum QKD system can also be hacked by eavesdropper. Then we'll talk about this quantum random number generator QRNG and its integration to our hardware, to our this control electronic hardware system. We have developed this control electronics for this advanced QKD protocols, and later we'll study about some analysis we have done on this practical challenges in field implementation of these type of protocols. So over here, the picture is Professor Richard Feynman. Actually, he proposed this new way of doing computation using subatomic particles like photons and electrons by using their quantum properties such as quantum superposition and entanglement. One can solve a certain specific type of problems that cannot be solved using classical computers, which is like search algorithms and prime number factorization. As we know that the RSA, a classical encryption method, is based on actually prime number factorization that can be broken by a source algorithm, which with the sufficient larger qubit size, it can be broken. Now the next picture is this is a this golden chandelier. It is a superconducting based quantum computer. Now, as we said, that security threat is imposed by the quantum, and when I say quantum, it is a nature, how a nature behaves. As I said, this security threat is imposed by a quantum. Solution is also given by a quantum itself in the form of quantum cryptography. Let's talk about the quantum key distribution. QKD is a secure symmetric key distribution technique whose theoretical security is assured by the laws of quantum mechanics such as no cloning theorem and the Heisenberg's uncertainty principles. If you want to see a traditional way of QKD, there is a two parties called Alice and Bob, which and theoretically Alice has a single photon source, or we can say a qubit that can be encoded in its quantum state. Information can be encoded in its quantum state, and that can be transmitted through this quantum channel. This quantum channel can be free space, and the fiber as shown in this picture. The first one is a free space or satellite based thing, and the other one is the existing telecommunication fibers that can be used, and the other side, the Bob actually decode the information encrypted by the Alice. As I have highlighted this thing, that there's a theoretical security or unconditional theoretical security, but there is a practical imperfections. And practical imperfections in the source side, imperfection in the encoding, as well as the transmission. We know that these fibers and free space, they are lossy channels, and at the end, this detectors vulnerabilities are also there. As I said, there is an imperfection. That imperfection in these physical devices that actually introduce the loopholes for the eavesdropper to get useful information from the Alice and Bob, or a secret key from a secret keys. To remove this loophole, we have to remove all the dependency from existing physical components. As I said, there are physical components are associated with this, and based on that, there is a DI-QKD is available. That is a device independent. There is no dependency on the devices. Based QKD systems are there, but the DI-QKD suffers with the highly complex system as well as the very low key rate. So, what is the alternative is MDI-QKD. As I said, the last part. MDI is a measurement device independent quantum key distribution. When I say measurement device, there is a single photon detectors that actually used to measure single photons. Whenever a photon arrives at a detector, it actually get a detection. So, but these SPD, this SPADs or single photon detectors are most vulnerable or weaker part of this entire QKD system. So at least we can remove the dependency from the measurement devices, and that is the part of this advanced QKD protocols, which is MDI QKD protocol. It removes the dependency from all the measurement devices present in the system. So as I shown in the fiber-based communication, this is as I saw these satellite images, they are far, far away. If you see this below image, so there is a central station, and there are two stations, Alice and Bob, that actually send their quantum state to a central station where they do certain kind of measurement known as the Bell state measurement. So this Alice and Bob in this picture, they look near, but actually they are far, far away, like hundreds of kilometers. I will explain all these blocks, what exactly they are doing. But in this slide, we will talk about this Bell state measurement. Alice and Bob prepare this using a weak coin source. They send this phase randomization technique. They send their quantum state to a central station that is known as Charlie, and Charlie performs the Bell state measurement. What is Bell state measurement? It is a 2 photon based interference measurement. There is a joint projection of these 2 photons on one of the Bell state. The Bell state is known as this psi minus Bell state. Bell state is nothing but the maximally entangled states. So this MDI QKD has the advantage over the different traditional QKD system like phase reference based QKD system like DPS and COW. It is immune to all the possible detector based attacks. This has this inherent star type of topology. So it is MDI QKD is the best suitable for the longer networks. More than two stations can be used as a single central station for performing this QKD. And also it sustained a higher channel losses because of this two photon interference. And as I said, this central station is actually an untrusted node. If Eve has the information and if Eve has the all the control over this signal, this station, detection of any of detector will not give any useful information to Eve, or it will not remove any, it will not leak any information for our secret keys. And it is highly practical protocol. Other protocol is a twin field QKD protocol. MDI has a single disadvantage, which is secret key capacity is bounded by a Plov bound, which means that the secret key rate is linearly dependent on the transmittance of the quantum channel. So this twin field QKD has all the features that MDI has. Along with that is the square root of dependency on the transmission of quantum channel. So this blue line is actually a bound that cannot be broken by any other QKD protocol, where twin field is actually breaks this protocol and gives a longer distance. So these are again, these two parties are there. They prepare the states, they twin states, exactly similar states, and send it to a central station where Charlie this time perform a single photon interference, a photon interfered with the vacuum, and announces the constructive or destructive results out of this detectors. Now let's talk about quantum hacking or attacks on the system. As I said, that MDI and twin field, they remove the dependency from the measurement devices. So our measurement sites are totally attack proof. But the source we are using is a weak coherent source, and it has a finite possibilities, such as there is multi-photon emissions are there. So for that, what we generally use a decoy state protocol along with the weak coherent sources. Weak coherent sources is nothing but attenuated laser source. It means that when we have a pulse laser source and we attenuate such a way that mean photon number per pulse is less than 1, and we can, along with this thing, we send a decoy system, decoy state. Decoy states is nothing but lower intensity signals. So any effect or any presence of E will affect this lower intensity first, and that can be monitored by the parameters of the QKD system. Okay, so as I said, this imperfection of the practical devices leaves the potential loopholes and E to spy the final secret key. So this is the approach which we can use it. But now the E is come with the new approach. This is together he come up with the two attacks. The one is the unambiguous state discrimination attack, and along with that he can perform a photon number splitting attack. Unambiguous USD attack is nothing but he can discriminate these single state and the decoy states, and whenever he perform this POV measurements on the system, and whenever he discriminate this state, he will not disturb this decoy state, and only get the, whenever he get the signals, he will try to perform the photon number splitting attacks and get the useful information. So this was again a threat, and the solution what is given by a security patch or a patch. Patch is something like whenever we have a loophole, we give a patch to it to remove any leakage kind of thing. So we come up with this, not we, but researchers come up with this phase randomization of weak current sources. So phase of this weak current source is if it is continuously removed, the CSD and the PNS attacks are not possible. So they are. So what we have done, we have experimentally done this discrete phase randomization of weak current source along with this decoy intensities. Now there is a word called random. How to bring a randomness in our source? So previously I have done some work. There is a quantum random number generation, and we can integrate it into our system. So there is a heralded single photon source. There is a nonlinear crystal. When we shine an intense light, occasionally some of the photon get down converted and generate a pair of photons. And these photons are actually shows that when we see the characteristics of these photons, they are truly single photons. And these are heralded single photon source because detection of one photon actually heralds the presence of other photon. Now we have these single photons, and when we send it to a beam splitter, it has a 50-50 beam splitter, and when it has a 50-50 possibility, either it can reflect or it can be transmitted. That's it is a transmitted. We can say okay, generate a bit 0, and when it reflect, we can say okay, it is a bit 1. So based on that, we can generate a random bit string. Although there is an imperfection, and we can do some randomness extraction. After extracting this randomness, it clears all the nest randomness tests. So remember that now we have a random bit string, and we are going to integrate it with our existing hardware system. So this is the overall setup for MDI QKD. There is two party, Alice and Bob. They are far away from each other. They use this CW laser and the electro-optical modulators controlled by this FPGA boards, and the QLD is integrated with this source. So I'll go faster. So this is a FPGA based control electronics architecture for our experimental data, experimental setup. This is a FPGA board. First layer is actually a AXI interface that can be user command interface. We can give a user command and get any information from this layer. Other thing is that whatever random number we have generated from the QRNG, that can be integrated using a I2C protocol using this peripheral modes. It can generate a RF signal, RF output signal. We are currently generating a 1 gigahertz signal. It is a 1 nanosecond signal with the very fine 4 picosecond shifting. Apart from this, the last layer is actually generating a multi-amplitude signal that I will show you in next slide. So these are our experimental results. So what we have done this discrete phase randomization with the CW laser and the electro-optical modulators. So when we these are 4-bit register values that are coming from the QRNG. So whenever a random bit 4-bit register will come, randomly it will select one of the phase slice from 0 to 2 pi, and it will randomize the phase. So we are doing in a 16 phase slicing. Apart from this, we are doing a phase encoding by using a 2-bit register. There are 4 different voltage output levels, and we can use this for phase encryption. Overall, this is the phase randomization optical signal. This is an optical signal. This has some 1 gigahertz signal and can be shifted very finely. Last one, this thing is there is a bound that with the slice we compromise with the secret key rate. So we have done 16, so we are compromising with the secret key rate, but we are increasing the security. There are some practical challenges in the field implementation, especially when we do the photon interference. So there are this majorly three type of things we have to see about it. First one is the temporal overlapping at a central station. As I said, central station is far away from both the station. We have to do a nice perfectly temporal overlapping. They need to arrive at the same time at a beam splitter, so they can perfectly interfere. And second thing is the polarization need to be identical for their interference. And the third is the phase of an optical signal need to be correlated, whether it is anti-correlated or correlated, whether it is zero phase or pi phase, that that need to be taken care by using a feedback system and different two protocols. So as I said, there is a phase evolution that can be because of the optical sources. There are two optical sources, different sources are used, so that can be phase locked by a single reference laser source using optical phase locking techniques. For that thing, both the lasers are locked. And the second thing is the phase introduced by the optical channel. I said we are using a longer fiber channels. There is a phase evolution by this optical channels. So currently we are at here, and we have generated our both the states using this FPGA based control electronics hardware. There are these two protocols or two techniques to overcome with this phase introduced by the optical channel. We can send a time multiplex signal along with this quantum signal, and based on this high intensity signal, we can actually manage to remove this phase evolution by done by this quantum channel. And second is the post selection protocol, where we can set an offset in post processing, and we can estimate certain parameters, and based on that, by minimizing these parameters, we can actually get a nice phase evolution and remove this phase changes. So if I want to conclude it, so we have generated this phase randomized optical signal. I can say it is an initial quantum state using this weak coherent laser and the electro-optical modulator. We also have developed this control electronics hardware for this MDI QKD protocols. Apart from this, we are actively doing in practical what is the field challenges for the field implementations for this kind of protocols. These are the references. Thank you, everyone.
Thank you, Mr. Mohit. Thanks for your very good presentation. With that, actually, the session ends.
Thank you so much, sir. Now I would like to call Dr. Anand Mohan to present Shri Dilip Burman, sir, with a memento. Next, we have an invited talk by Shri Abhishek Ranjan, consultant Pantasign CA. Abhishek is a seasoned tech leader with experience in building large-scale government technology projects. He previously served as the CTO of CSC e-Governance India, India's largest front-end service delivery network, and was a key member of the team that developed Aadhaar, India's national identity card system. His contributions to Aadhaar included developing the biometric attendance system and digital life certificate. Abhishek holds a bachelor's degree in engineering from BITS Meshra and specializes in product strategy, technology planning, and leadership. I would request Shri Ashish Banati, Deputy Controller of Certifying Authorities, to felicitate Sir with a shawl. Yes.
Thank you so much, sir. Thank you for the opportunity. Good afternoon, everyone. My name is Abhishek and I'm a consultant with Panther Science CA. And I'm going to present a talk on building secure foundations. Shit. It is not. I think I will run the PDF. I have a PDF one.
चलेगा.
हाँ ठीक है. So my topic for the day is building a secure foundation using the hardware root, attestation of trust, and PKI combined together. So this is something which is not new. However, we see and use it on a day-to-day basis and experience in our lives. But we are trying to come up with a solution which we are trying to move to implement at a central level to safeguard the do something at the country initiative. So why do we want to build a security foundation and why it is important? So the most important factor is that it helps us and gives us security and protection for the data and information that we have. So with the large advent of digitalization all in the last decade, what we see is that we have been using digital on every aspect of our lives. It's like we say that digital is a part of life, but I would like to say that it's more of a way of life now, and we're thoroughly dependent on digital devices. So it is important that we safeguard those information and data like our personal information, our financial information, a lot of other things are there. So a security foundation helps us alleviate those risks and gives us a better security posture and gives us a long-term resilient to stay aloof from such threats. So the components that we are talking about is building a centralized attestation system, and the core components of a centralized attestation system is a hardware root of trust, which is the security foundation of any device. It is the secure foundation of any device, and the key function of a hardware root is that it establishes trust between the different components of a computing system. That is, we can say it's primarily because of its key features like it is immutable, it does not allow any malicious code or alterations in the boot, and allows for a secure boot of any device. Secondly, typically all the hardware roots are capable of performing cryptographic operations like key generation, storage, and other functions like signing and all. And then again, it acts as the trust anchor. That means that any security protocol that is happening on the device is actually enabled through the hardware roots. So typically the trends or scenarios where we see the hardware roots in actions which is coming up is the IoT devices, which is like major changes in our ecosystem. We see a lot of IoT devices around which are have chip-based controllers and all. What we want to say is that we should have a secure communication channel for all these IoT devices to connect and communicate with the central systems in a secure manner. Similarly, we have critical infrastructures that is like healthcare, energy, telecom, finance. They're all adopting hardware roots to have a secure environment to ensure that the applications that are running and operating on such network or systems are secure enough that it does not allow for any tampering, because we're largely dependent on it. Secondly, thirdly, we see that cloud and edge. So we have been used to these OTT channels and all, and a lot of other things are coming up. And most of them are using edge computing now to give you the data at the nearest pop, so that you get access to them, the data or information that you're trying to access on a very faster manner. So the process of data share between all these components together, the hardware roots again are playing an important role there. Like Amazon is a large use case, Azure is a large use case which are using this. Similarly, with the advent of AI, we see a lot of AI coming in with Gen AI and all, and largely many of applications are also evolving which are depending on these AI outcomes. So the outcomes should not be untrustworthy or where we can rely on without any assurance. So the hardware roots will actually add up an assurance level that the information or the outcome that is coming off such AI systems are something which is trustworthy enough that we can rely on to make decisions. So attestation of trust is another component of what we're talking as the central attestation service. So attestation of trust is a secure process for any devices that we're talking about today. So that when they connect or when we are using, so attestation of trust is a mechanism, it's a secure mechanism which allows to validate the integrity of the device cryptographically. So what we intend to say is that there are typically three, on a very simple manner that I've tried to explain here, that we see there's an attester, the person who's actually the originator of the data or the information. Then we have a verifier system, and then we have a relying party who's going to consume the information that we are passing on. So now what happens is the attester would push a request to the verifier, which is a attestation evidence, and the verifier would sign up and give the verification result back to the attester, and then again that is relayed back to the relying party, which is the attestation result, so that they have an assurance of the information or data that they're using is actually thoroughly secure. So the prime functions or key features, you can say, they are give you a security assurance, they establish trust, and they also help you to be compliant and be integral. So the large use cases, what we talk about attestation of trust is some of the most popular ones, because all of us here would definitely be using a mobile phone, and in some or the other manner we are every day using this attestation of trust service. Largely two of the most prominent ones, Apple and Google, because most of the phones are today either Android or they are iOS. However, there are other examples as well, like Apple, Microsoft, Amazon and all. So there are two features which we can say about the Apple and Google implementation. So all the Google phones today, they have a attestation or a hardware trust, which is actually a TE based, which is a trusted execution environment. It's again a FIPS certified, and they ensure or assure that any application that we are installing or devices that are connecting are thoroughly secure, and they connect to a centralized Google Attest Play Secure services, and they come back. However, Apple has got just the same implementation, but on a different style, that they are more on the platform, or you can say it's a TPM based, it's more hardware like, and it is also a FIPS certified, and they also do the same thing. So any application or any information that you're storing on your Apple devices, they are thoroughly secure above some of the certain ranges, like say they say that above 11 iPhone 11, they got a dedicated security controller within the device itself. And on the Android side, we see the larger or the higher end models, they have such implementations. So what we're saying is that the three concepts, the hardware root, the attestation and PKI, they can combine together to build a combination framework which can particularly help us challenge or particularly context the evolving threats like quantum computing. Like they give us an enhanced security with the multi-layered defense. They help us build all the trust and compliance requirements that we have, and also future-proof ourselves from the next generation of cyber security threats or challenges that we may face. So this is the main one that I was talking about, that we propose or move to build a central attestation service, which is to maintain a centralized record of controllers that manages the trust request from trusted devices within the country. So why? Because we talked about the threats and all, and similarly, number one, we said that most of the devices that we use are not in our control. So there may be a chance that we may lose to impersonation or lose our device hijacks and all. So building a central registry would actually help us alleviate us from such unknown threats or thorough dependency on external agencies and all. So the central registry is one which stores all the hardware roots within the country. It gives us an enhanced security, threat protection, and then again what we say is that we should embed the PKI within it, that the CCA root, so that it becomes a non-repudiable trust instance. So I have done a basic concept architecture of the CAS system, which says that there's a there's a device which is originating the request, or they're coming into the network. So they pass on the registry information or the image of the device for a registry registration of their devices. So these are basically a layer of, set of REST-based APIs, which can be thoroughly authenticatable, that any device or application that they're talking to secure APIs. And then they first, whenever they send a request, they would actually get into the registry, which is maintained at the centralized layer. And then again, whenever a attestation request is sent, that again is forwarded to the trust gateway, and from the trust gateway it goes to the device check whether the device is available, the information keys are there or not, and then it gets signed up, and then it is returned back on the same channel to the requester, and from the requester it is on a different channel sent to the relying party, and the relying party on a different part sends the request back to the trust gateway for a verification of the attestation, that the attestation response that was given by the CAS is again verified on a different path. That makes it a thoroughly secure fundamental framework, that the verification request, the signing request and the verification request, both of them travel in a different path and make them highly secure. So that was the flow. Some of the challenges that we see to build up such a network or a framework in the country, that the policy has to mature, with the government policy and support has to come into the picture. There has to be a lot of OEM cooperation or the chip manufacturers cooperation for getting those trust roots to be built inside the registry. And then we have to have a timely development to get this framework in place, because of the advent of the quantum threats coming in like another 2 years, what we say. And these are some of the advantages of the CAS, that it will ensure and enhance a national security, and ensure that only trusted devices and applications operate within the country. So some of the features like application key advantages like application security, quantum, it becomes a quantum ready system, and then it also allows us for a seamless migration from the present system to the quantum ready system, that it gives us time and a lot of advantage in terms of the migration cost. It helps us reduce the cost of migration to the quantum era, and also saves our time. So, and all these through a robust communication platform or an instance within the country. So with this, I will end my talk. I thank you so much for the time, and thank you for having me here, and thank you CCA sir and Deputy CCA sir for the opportunity to speak here. Thank you so much. I'll take my, thank you. Okay. Okay, you want to take the PPT? Sure.
Thank you, sir. I would now.
Send you on the WhatsApp. I will send it. I got it. Okay.
I would now like to request Shri Praveen Ampat, Scientist E, CDAC Bangalore, to felicitate sir with a memento.
Thank you all. Now we'll break for lunch. But after lunch, we have our international speaker, Mr. Alexei from Russia. He will be talking about quantum PKI. And then we have another talk by Professor Devdeep Mukhopadhyay on post-quantum. So please join us back. And after lunch, we'll also distribute the kit bag. Thank you.
You had your test? No. पालन करके है ना यहाँ पर
Thank you. Thank you so much.
Thank you. No, it's not working. No, it's not working. I think it was not fully copied. Ha. So where is the?
Yeah, this one. Hello, let's go. This one. Slide before that. Yeah, this one. Can you just see where it plays? Yeah, there is. Can you search? There's an audio.
330. No, इसको तो slides so
Good afternoon, everyone. For the first session post lunch, we have a lightning talk by Shri K. Srinivasan, CISO, Watch Data Technologies Private Limited. The title of the talk is Overseas Payment and Authentication Product Development and Support and InfoSec Compliance Requirements for India Market. Chip card and security domain expert having over 20 years of experience in payment card technology and its data security aspects. Shri K. Srinivasan also has over 7 years of experience in handling ISMS or risk management processes of banking technology. So please. I would like to request Dr. Sanjay Adiwal, Scientist E, CDAC Bangalore, to felicitate Sir with a shawl.
Namaskaram. So good afternoon, everyone. So basically, I would like to thank CCA and CDAC for giving an opportunity. So it will be, as they said, it will be a lightning talk. I just prepared for a quick 5-minute session just to share about an OEM contribution in this PKI domain. So I'll quickly get into the slides. So just a quick introduction about watch data. So basically a smart card vendor. So number 4, top 4 smart card vendors in the world. So we basically into manufacture smart cards, SIM cards, and payment devices, as you can see, and also crypto tokens. So we are in existence since 30 years, and our Indian entity was set up in 2007. And so primarily our core strength is the card operating system and related software and solutions. So just quickly getting into the crypto token product suite. So we have basically come across a long way in terms of the crypto domain. So in fact, internationally, we have started this product development somewhere in 2005. And so over a period of time, we have come across 4 generation of tokens. Okay, and primarily the first generation token is in the Indian market now. So, so this just images of the product. So basically that's a standard version of token. The second version of generation of token is called a sign what you see token, wherein the challenge response or the data that you are signing it can be visually seen by a display and you can just confirm it. And the third generation is more about a QR based challenge response or an OTP or a signed response based token. And the fourth generation is mainly on the to cater to cross-platform devices and mobile devices like tablets and mobile phones. So that's on Bluetooth platform basically, and also with the biometric.
Hello. Hello. I request you to kindly keep quiet. Hello. I request you to kindly keep quiet. Thank you.
So coming to the Indian context, so basically we had a very humble start in 2014. So we started our supplies of crypto tokens called PKIA, which is on the leftmost side. So that's what we start. So with the help of CA eMudra, so we partnered with them. So we launched our product in 2014. And in the process, apart from traditional usage of DSC applications in 2014. We also wanted to explore options of using the crypto tokens in the other domains, especially in the banking domain, okay, and use this as a device to secure the banking transactions. So we did some trials. So those are the images you can see, trust factor token and trust key token. It's basically jointly we did with eMudra, and we did some pilots, but we realized that we were literally ahead of times, wherein there was a challenge in accepting the token in the ecosystem itself. There were many challenges in even accepting the token, making it work on an end user point of view. So what we did is, so we focus more on supporting that ecosystem so that the token can be easily usable. So we started focusing on improving the software side of the token, so-called, the drivers or your admin software, which comes along with your token. So basically we enabled features like, automatic installation of the driver, auto update of the drivers, and then automatic configuration of the Java settings or any other browser settings, ActiveX control settings that you need to do. So that can be done seamlessly so that the end user doesn't have to know about what they need to do. So they can simply plug and play, and then they can just start using it, and also integrated some of the other applications like, Office document signing and PDF signing. So, so this basically in last 10 years, so we have stabilized the product. So, and we have gained a good market. So in fact, I'm proud to say in last 10 years, so we have supplied over 12 million prox key tokens in the Indian market. And now, so we just wanted to look forward to the newer plans, basically. So on two things. So one is obviously to align with the vision of the Government of India, Atmanirbhar Bharat. So we have already certified a token based on an NXP platform, so which is FIPS 140-3 and CCEL certified. So using that module, so we are also working on some mobile PKI solutions. So positively, we would want to launch the product by end of 2024. And similarly on the PQC line, so we have just, we have our own suite of Internet of Things and Internet of Vehicle products, wherein we are into that domain in terms of the supplying the OEM hardware and the solutions. So we have developed our own TGM-OS. So while designing that, we have also considered PQC, so that whenever there is a demand from any regulatory perspective or any demand business needs, so we can implement those functions in our OS. So that's all from my side. Thanks. Thank you for this opportunity. No, this got certified in BIS. Yeah. Yes.
Thank you so much, sir, for the compelling session. I would now like to request Sri Arvind Kumar Sharma from Office of CCA to felicitate sir with the memento.
Alexi is there.
Thank you, sir.
Thanks.
Next, we have invited talk by Fedorov Alexei, Head, Institute of Physics and Quantum Engineering. Dr. Fedorov Alexei is the Head of Institute of Physics and Quantum Engineering at National University of Science and Technology, MISIS. He has an Information Security Engineer degree from Bauman Moscow State Technical University. He also has a PhD from Paris-Saclay University, France, in physics and mathematics. In 2020, at the age of 26, he became a professor at the Russian Quantum Center Department of the Moscow Institute of Physics and Technology. In 2021, he won the Fidelity to Science Award for his contribution to popularizing science and technology among young scientists. In 2023, he became a member of the Coordination Council for Youth Affairs in Science and Education of the Presidential Council for Science and Education. I now welcome Sir to start his talk.
Yes. Hello, and thank you very much for so kind introduction. So let me try to share my screen. So can you see it now?
Yes, sir, it's visible for us.
Yes. Thank you very much. And I was asked to focus more or less on our activities related to quantum cryptanalysis and developing quantum-resistant cryptography tools. So basically, it's more or less well known that quantum computing possess one of the threats on the currently existing cryptographic tools, especially ones working on cryptography based on public keys. And in this regard, we work in several directions. So first, we, with our colleagues, develop quantum computing devices and try to push the limits of their performance. Then we worked on cryptanalysis. So we worked on creating new types of algorithms for quantum computers that allows use them for analyzing security of cryptographic algorithms. And finally, we developed several directions in quantum-resistant cryptography. So on cryptography, which believed to be useful and believed to be resistant, even having in mind that our adversary has a powerful quantum computer. So I will first start about our activities on quantum computing. And maybe one of the key points that we explore here is the fact that we use QDITs. QDITs are multi-level quantum systems. And this is related to the fact that in classical information theory and in classical information technologies, we are heavily based on binary information encoding. So we have basically 0 and 1 as main paradigm bits that we used everywhere. However, quantum processors, which we used in our current experiment, allows us to encode information in much more rich structures with many energy levels, which means that we can use them not for binary encoding, but for much more complex encoding systems. And many platforms that are now used to build the quantum computers are actually helpful, and they allow one to encode a system in a much more complicated way. So here presents several examples of quantum processors that are now under the development in Russia based on superconducting circuits, atoms, photons, and trapped ions. And all of these systems can be used not only for binary qubit encoding, but also for QDIT encoding. And the crucial question here, whether we can get some advantages by using these systems in the QDIT setup. And there is a large progress in this direction across the globe. So many institutions work on building quantum computers with QDITs, for example, based on trapped ions with up to 7 controllable levels. So instead of 2, we have 3, 4, 5, 7, and more in United States, in China, and there is a large portion of scientific activity around this direction. So we also worked on that experimentally, and that's our joint work with my colleague Ilya Semeryakov, who built in Russia multi-QDIT quantum processor, where we use 10 ions, 10 qubits, in order to perform quantum operations. And the basic idea that part of these operations we conduct not between two different ions, but inside one physical ion. And we use ytterbium ions with many, many levels. And we have such ability in our experimental setup. So that's how it looks like now in practice. So that's the most powerful quantum computer built up to now in Russia with 20 qubits, worked on QDITs. So each shining dot here on the screen is individually controlled trapped ion, which we can use for encoding information. So one of the things that we would like to do with a large-scale quantum computers is actually factoring. Yes, so finding prime numbers with quantum computing system which automatically possess a threat on a quantum computer. So in this activity, based on the idea of using quantum technologies to break cryptographic algorithms, has already like more than 30 years. And it starts from famous algorithms proposed by Peter Shor in the middle of 90s. Unfortunately, this idea, based on the direct application of Shor algorithms, required prohibitively large amount of qubits. So as I mentioned, we work with dozens of qubits now, but in order to break cryptographic codes with quantum computers, we need millions of qubits. So millions, which, much ahead of what we can do now. That's realistic estimations that in order to factor 2048-bit RSA integers in 8 hours, we need about 20 million of qubits, assuming that we do error corrections with the parameters that are presented on the slide. So that basically means that in principle with quantum computing you can do so, but it's hard to imagine when we will get such a quantum computer in practice. There are, of course, other attempts to optimize that. For example, recently, several papers were published on arXiv related to reducing the resources that would be needed to use factoring and computing discrete logarithms with quantum computers based on optimization of the Shor algorithm. And that's mainly done by Regev and extension of his work, but still it's currently non-clear would it be lead to improvement in the physical implementation and how many qubits we will need, and raw estimation, and still we need hundreds of thousands of qubits or so in order to implement such quantum algorithms. And very recently, about a year ago, a couple of years ago or so, a large group of scientists, they proposed to use currently existing and upcoming generations of quantum computer in order to factor. And they demonstrated that with the use of combination of classical Schnorr's algorithm, so don't to be mixed with Shor algorithm, and quantum approximate optimization, one can get significant improvement in factoring with less amount of resources. So basically, they estimated that with quantum computers of about 400 of qubits, it would be necessary to break RSA algorithms of the more or less existing standard. So that's, of course, was sensational announcement, and we started to go deeply and deeply to understand what's going on. So it works like that with classical Schnorr algorithm, we selection a factor base, finding smooth pairs, so-called SR pairs, construct linear system of equations with that, and construction of factors from these solutions is based on just Fermat's approach. And the problem is that the search was this as SR pairs, they can be done as solving shortest lattice vector problem, which in turns can be solved with so-called LLL algorithm. But that requires significant amount of resources. So what has been suggested is to reformulate this problem as quadratic and constrained binary optimization problem and use quantum computers to solve this optimization problem. And the assumption is this factoring can be accelerating when this SVP problem, shortest lattice vector problem, is solved by quantum computer. So that's in more details how this quantum approximate optimization algorithm works. So basically you prepare some quantum state and then optimize it unless you will get the solution. And solution in this case is just this vector that we need in order to factor. But as we realize, it seems that it doesn't work mainly because of many pitfalls that exist in this algorithm, and we demonstrated it. And also recently, colleagues from Google also, pointed out that this approach would not work. So one of the things is that this classical feedback loop sometimes kills all the potential advantage that we have, and sometimes we don't see even any convergence of these algorithms to the solution. So you see here that it doesn't go to 0. So so basically random search in this case becomes more efficient rather than this approach. So seems it is not scalable. So I would not go deeply into details. If you're interested in, I would be happy. But in our paper, we summarized and formulate the main results of our analysis. So in which concrete cases this would not work. So what we propose to do in order to make it better, we propose to kill this classical feedback and basically use these algorithms in a bit different way when we used these parameters that we need in the algorithm by calculating on the training samples and a unitary evolution algorithm, which makes this approach is much more efficient. And by that, we demonstrated it experimentally that for small scale quantum circuit, we can use about 10 qubits in order to factor about 1,000 scale number. So my point would be that this approach in general can be saved, but still needs to be investigated. And there's still the question about the amount of the resources that would be need in order to factor something realistic is needed to be further investigated. But it's interesting avenue. So here we demonstrated that we work with better than random sampling and work with even larger numbers. So about our activity about quantum resistant cryptography. So I'm not really sure how much time actually I have. So from organizer, I heard that about 10 minutes or so. So I'll use the rest of my talk just give a brief overview what we have. So first, we developed a high-speed quantum key distribution system, which use single photons in order to encode information and send it between receiver and transmitter. We demonstrated the full security of this protocol by presenting a security proof. We demonstrated the level of practical security, so basically the absence of side channels with these devices, jointly with Vadim Makarov, who is known as quantum hacker, the guy who is able to hack even quantum things. Best possible post-processing procedure we developed by our team, and still it's record in efficiency for certain aspects. And we have simple version of this device for research, development, and education. So we work intensively of building quantum networks, so connecting different, devices connected via infrastructure, and we created some switched-based network system which allows to reduce the amount of resources that is needed to build such quantum network. So we also worked on space quantum key distribution. So we already launched a transmitter prototype which allows to send the signals from the basically space to ground, and work now on testing it and connecting with this device from the space. So the basic idea is that this satellite can be used in order to send information for generating quantum keys. And finally, so let me mention that we also worked on post-quantum algorithms. So post-quantum algorithms are actually classical algorithms that are resistant and against the attack with quantum computers. And we have fully integrated library compatible with OpenSSL containing the best currently existing quantum resistant algorithms. And these things can be used in any platform and already can be tested. And also we have solutions based on that, for example, tunneling of the traffic using post-quantum algorithms for browser extension, proxy service, reverse proxy, and things like that, which can be integrated in any also IT application that we have. So basically, I believe that we live in the very interesting period of time when we understand that quantum computers are progressing, and with these capabilities, indeed, classical ways of securing information needs to be reconsidered. And there are two approaches which we find complementary. On the one hand, quantum key distribution, which will be great for securing information, for example, between data centers and some critical infrastructure, and post-quantum algorithms, which can be easily integrated in any user applications. So that's basically what I would like to present it, and let me go to the the most important slide of my talk. Thank you very much for your attention.
Any queries are there? Okay, so there are no queries. Thank you, Alexei.
Thank you very much for my attention, and greetings from Russia. So have a nice conference.
Thank you.
Thank you.
Next, we have an invited talk by Professor Devdeep Mukhopadhyay, Professor of Computer Science, IIT Kharagpur. Professor Devdeep Mukhopadhyay is an Institute Chair Professor at the Department of CSE, IIT Kharagpur, India. At IIT Kharagpur, he initiated Secured Embedded Agricultural Laboratory SEAL, focusing on hardware security. Prior to, he was a visiting professor in the School of Computer Engineering, NYU, Abu Dhabi, and had visiting positions at NTU Singapore, NYU Shanghai, and Brooklyn. He was also an assistant professor at IIT Madras and held an adjunct position at IIT Bhubaneswar. He holds a PhD, MS, and a BTech from IIT Kharagpur. Dr. Mukhopadhyay has published more than 250 papers in peer-reviewed conferences and journals and is in editorial boards and program committees of several top journals and conferences. He is the recipient of the Shanti Swarup Bhatnagar Award 2021 for Science and Technology and is a fellow of Indian National Academy of Engineers. He was a fellow of C3I Hub, Innovation Hub of IIT Kanpur, and has been enlisted in Asia's Most Outstanding Research compiled by Asian Scientist magazine. He was awarded the Qualcomm Faculty Award 2022, Khosla National Award from IIT Roorkee 2021, DST Swarna Jayanti Fellowship 2015-16, INSA Young Scientist Award, INAE Young Engineer Award, an associateship for the Indian Academy of Sciences, and a senior member of IEEE/ACM. So please. I would like to request Dr. Anand Mohan to felicitate Sir with a shawl.
First of all, thank you very much for this kind invitation and also for this kind introduction. So I will be giving this talk on post-quantum cryptography, but from the point of view of hardware security, which is essentially the area that I work on. So this is, like the lab that I essentially run in IIT Kharagpur, which is called as a Secured Embedded Architecture Lab. Our focus has been on attacks and countermeasures, specifically on the domain of hardware security and cryptographic engineering, which tries to take, like the theoretical foundations of cryptography and implement them on real life devices. And I've been happy to, graduate several very, good PhD students for whose good work, I'm presenting this talk. So this is how we started with working on. So we initially started to work on VLSI of crypto systems, worked on formal verifications for finite field circuits. Side channel analysis and countermeasures have been some of the central areas of our work. We also looked into post-quantum crypto implementations and still are looking into that because of its importance, as this conference also stresses upon. We have been working on microarchitectural attacks, Trojan designs and detections, physically unclonable functions, applying them on IoT security, machine learning for attacks and defenses, something that you cannot stay away these days away, cyber physical system security. And recently, I'm also interested in physical hardware assurance by imaging of hardware devices, and also privacy enabling techniques, where many of these post-quantum techniques can be very nicely applied. So I will give a very quick demo of our lab. So here is a quick view that you can have of our C lab. Hopefully it works. There is an audio. No, it's not working. There should be an audio. Okay. So this is a sort of a setup that we have in our lab, where we are trying to kind of develop a hardware forensics setup. As you can see here, that there is a scanning electron microscope, a FIB, and also an X-ray microscope, which we use to kind of monitor and kind of see into your hardware devices. And as you can understand that with this infrastructure, the objective is to look into the chips. Okay, so you can think about your small integrated circuits, maybe in your credit card. And what we are interested is really to kind of look into the device and see what kind of crypto circuits are really implemented. Okay. And the objective of this looking into is because of several hardware security threats, something that we call as hardware trojans, because many of these devices or chips are fabricated at foreign shores, and we are always curious to know that whether they are exactly doing things that we want them to do, or essentially have something which are called as hardware trojans. So we do these imagings using also X-ray microscopes or XRMs, which essentially can probe your PCBs or your designs, which you can use in your data centers and other application areas. And what we are looking into is whether these devices have components which can be potentially malicious. So this is one of the central thrusts of our lab, and we also have been, of course, working on things which are more classical hardware security problems, which are called as side channel attacks. I think so here are some pictures that you can see of PCBs which are being got from different sources. We are also looking into other applications, like for example nowadays security and cryptography have got several applications in the power security domain. So we are also building out infrastructure for performing security evaluations of smart grids and other real-time systems. We are of course interested in side channel attacks and fault attacks. So I think today morning we had a talk briefly being spoken by Anshuman where he was mentioning about fault attacks. So we are also looking into your chips, and which are basically protected by the cryptographic techniques, and we are curious to know that whether they can be broken by side channel evaluations or so. Our main objective is, of course, not to break the devices, but really to protect them and to kind of develop countermeasures which can potentially thwart such kind of attacks. So although we initially started to work on devices which are more, I would say, tailored for side channel attacks, but recently we are working on more real life devices which essentially are deployed in a commercial fashion. Okay. So here are, and many of these hardware security experiments have to be done at rugged environments. Like for example, this is a temperature chamber that evaluates some of our hardware security primitives and kind of, evaluates them at various temperature points. So this is an example of a fault attack setup that we have. I think Anshuman was mentioning about fault attacks. So we'll try to give you a quick view about how fault attacks work. So for example, here is a a setup that you can see with an electromagnetic probe, and there is an amplifier through which we can kind of amplify the the EM pulses, and you can inject faults in circuits. Okay, so this is a kind of very quick overview about some of the lab infrastructure or hardware security that we work on. So with this background, I would rather get to the problem that we are discussing here, which is on post-quantum. We call it post-quantum cryptomania. Okay, because we know that the fear or whatever the apprehension of quantum computers essentially makes many of the foundational problems on which our current day public key resides vulnerable, and therefore we look into potentials where we can develop cryptographic algorithms which are resistant even in the post-quantum crypto world. So if you look at what I will try to do in this talk is come up with I would say a 5-point recipe or 5-point step of how probably we can go ahead in designing post-quantum crypto, not only from the theoretical point of view, but also maybe from the practical point of view or practitioner's point of view. So what we want from cryptography is, of course, we want informally to protect our confidential data for being recovered by an adversary, And for that, we often rely on hard mathematical problems. But however, most of these problems are based on assumptions that, like the smartest algorithms which are existing in the world right now, they are not able to solve them in an efficient manner. So we call that in terminologies of computer science as polybounded in time and memory. Basically what it means is that they are efficient. So now when we look at quantum computers, or the problem or the post-quantum world is that the quantum computers can solve many of these classical hard problems in an efficient manner. And therefore, when we step into the post-quantum world, we need to kind of develop techniques which are not only resistant against classical adversaries, but also quantum adversaries. Slightly formally, we call them being, like resistant to random oracle models, which essentially tries to kind of, simulate, I would say, an adversary in the classical world, and also what we call as quantum accessible random oracle models, which tries to model a quantum adversary. So in these both modes of adversaries, our system should be resistant. So for this, a potential roadmap could be envisaged in this manner. So in step 1, we define a new hard problems, or a set of new hard problems, which are secured in the ROM or the quantum random oracle model, security models. And in step 2, we try to develop crypto systems on top of it. Now again, like the statements are based on similar reductions that we see in the classical world, but now we are only relying on hard problems which are kind of believed to be secured in the ROM and the QRM security models. And in step 3, we come up with parameters which can be, used by these crypto systems for practical deploying, for efficient implementations in software. But many of these algorithms are so complex that to make them real life, or make them work in real life applications, you need support of hardware or hardware software co-design. And in this context comes the gap. Okay, comes the gap where adversaries tries to monitor things like side channels, like the power consumptions, the electromagnetic radiations, or maybe the behavior under faults, which can be used to kind of catastrophically break these crypto systems. So let's try to kind of take a very quick journey through these 5 steps. So in the first step, as I said, we need to define new hard problems. And as I think we have already been discussing about various types of hard problems like code-based, multivariate-based, and lattice-based. Of all these problems, like their classical counterparts, I would again emphasize, are all assumptions. Okay, so they are just believed to be impractical. So in particular, I will take a little bit of time to talk about lattice, because the hardware that I will be talking about is based on lattice hardness. So we know that lattice is the regular array of points in space, and just to give you a kind of a quick view, probably it will look like this in a 2-grid in XY directions. And now what we essentially have probably like a basis which we can use to describe the lattice. And then we come up, suppose once we have decided upon the basis for the lattice, we are given a point P and asked to find out the lattice point Q that is closest to P. So now, while in the XY direction, it would probably not look very daunting, but the moment you start increasing the dimensions, this becomes harder and harder, or is at least believed to become harder and harder. So this is called what is known as the closest vector problem, and so on. Like there are multiple similar problems which are believed to be hard in the ROM and in the QRM model. So noise and hardness has got a very nice association, it seems. Like if you take the very common algorithm like the greatest common divisor, which we probably all solve in our high school days, the problem becomes quite intricate when you introduce a little bit of noise, and this is called as the approximate common divisor problem. So the problem is that you essentially, if you little bit add noise and again ask for and generate what are called as approximate multiples of numbers, then finding out this GCD becomes more and more difficult. So this is exactly like the problem that we deal with. For example, here is a system of linear equations on the left, and on the right hand side are noisy versions of them. So it seems that solving the noisy versions are quite difficult. Like, just to give you a very simple example for the uninitiated, like suppose you take a system of linear equations, and if you add a little bit of noise, as you can see here, and therefore these are not equalities but approximately equal, then the solutions can be significantly off from the actual results. And that apparently makes the problem more and more difficult on which you believe you to develop these problems. So for example, on the left hand side here, you can see a box which has been created using these noisy versions of samples. And on the right hand side, these are some random versions of the sample. And now, as we say, do in cryptography, we come up with various versions of them, like decisional problems or search versions. And these are believed to be kind of, like that even in the quantum world, we will not be able to distinguish between them. And that is what is called as the famous learning with errors or the LWE problem. So once you have defined or discussed about these problems, you need to kind of look into the hardness. For example, the hardness could be whether it's in the average case hardness or whether it's in the worst case hardness. Now, interestingly, lattice-based problems have probably worst case to average case reductions, and therefore they are pretty promising. On the other hand, when you implement these lattice-based schemes, you can also kind of nicely avail the nice ring structures and use techniques which are called as entity or number theoretic transforms, through which you can get efficient implementations. Of course, code-based and multivariate systems, although they are lesser explored, have got also a lot of opportunities, and they are gradually coming up and becoming more and more researched. So the next thing, as we discussed, we have to kind of come up with the parameters, for example, the size of the key, the ciphertext dimensions, and so on which the crypto needs to be built. Now, once you have done that, you would like to build the crypto systems on the hard problem. And usually, as we will see that for many practical crypto systems, you have got techniques which are called as the key encapsulation mechanism, through which a session key is often established between parties, and digital signature schemes, which essentially are used by the counterparts to sign and verify the signatures. Of course, post-quantum, along with it, and often lesser stressed, comes up with several other applications like privacy enabling techniques, where we develop techniques like fully homomorphic encryptions and so on. And along with it, there are, every day there are new crypto systems that are being built. So just to give you some examples, like key encapsulation mechanisms, as we know that NIST is currently standardizing it, but there are always, several algorithms every day being published, which are based on these notions of hardness. Like, just to give you some example, Kybert is a famous lattice-based algorithm, which has been chosen for KEM for standardization. So likewise, for digital signature schemes, you have got techniques like dilithium and so on, which are used or are very popular and being chosen for standardizations for signatures. So after this, we would like to set up, the parameters, and this is extremely important, because on one hand, if I go for, and it's always a trade-off between security and efficiency, because if you choose small or conservative parameters, like we have seen in, several contexts, like, for example, we have seen in pairings, for example, which is known very well before. If you choose, small and conservative parameters, then often they have been broken by adversaries. On the other hand, if you choose large parameters, then your techniques or implementations or your solutions becomes inefficient. And, although you can kind of reasonably be sure about their security, but they are not very efficient. So therefore, the first choice could be that I choose very large parameters and I throw away all the compute power and parallelizations that are possible. Now, when we talk about resource constrained devices, like we were talking about lightweight public key, then this is not a nice strategy. And therefore, for that, we would probably try to kind of squeeze out the bit securities and efficiently do the trade-offs so that we can, implement them based on available compute power. And this is really, really a challenging problem. So in order to address the second, objective, we probably need hardware support for post-quantum protocols. And this brings us to the famous TLS-based architecture. Now in TLS, we know that it's a very common standard protocol for establishing secure communication on the internet. And classically, although, there are three very, I would say, clearly distinguishable parts, like the first part being the connection establishment, the second is the TLS handshake, and the third being the symmetric key cryptography. Now, we know that when we talk about the post-quantum problems, then the TLS handshake is the part that we need to address. So we wanted to investigate upon this and come up with a variant which we called as a post-quantum TLS and try to kind of protect it against the quantum adversaries. So we try to look at, again, the algorithms, and in this context, we basically pin down upon these two algorithms. One of them is called the Kyber and the other one is called the dilithium. So this was a part of an MS student that one of my students was working on, and we try to design a KGP PQC TLS, which is an agile post-quantum TLS accelerator, which encompasses, I mean, this is one point that I would like to stress, that because of the fact that quantum algorithms are getting compromised, we would need, even although we are going into hardware designs, you want agility. You want them to be supporting not only about, like various algorithms, but also at the same time various security margins or security parameters. So therefore, our technique to implement this was essentially based on microcodes, which means that you would like to kind of implement them using like specialized instructions, and although it essentially like has the benefit of hardware, the underlying implementation has a lot of flexibility. So we came up with a design, and this design, in this design, we particularly looked at the various optimizations that are possible. Now I will try to give a warning here that optimizations can be really dangerous if we do not really understand the inner reasons for them. For example, we know that usually in this quantum in these implementations, there are repetitive computations, and one of the reasons why they are there because of certain security requirements, like what is called as the CCA2 security. So we cannot really remove those kind of redundancies, which otherwise would look like nice place for I would say like optimizations that are not knowledgeable about the underlying security. So therefore, the rule of thumb is that never optimize the algorithm, but try to kind of optimize the implementations. So in this context, let us try to take a quick look at Kyber and dilithium. This is a like a KEM algorithm. It has got steps like key generation, encapsulations, and decapsulations. And these are some of the parameters that Kyber has. Okay. And our implementation kind of caters to all these parameters. At the same time, we have dilithium, which is an algorithm of a different nature because it's a signature generation and verification algorithm, and it has got its own nature of parameters. So the first question that we needed to kind of address is how do you really combine this? So here we come up with a crypto coprocessor, which tries to kind of share the dilithium and the Kyber data paths and come up with like a memory-based orientation of these steps so that you have got a combined KEM and at the same time a combined signature generation, which you can really apply in your TLS implementation. So we implemented this in a data path, and I'm just trying to kind of give you a very rough overview for the sake of time. So here we have got a hash unit, and there is a sampler, which is a very important component of our post-quantum implementations. Then you have got the entity multiplier, which I will a little bit talk about in my next slides, which are extremely important because they're the heart of your crypto processor. So what are entity multipliers? So just to give a very quick overview behind this, if I take two polynomials, and we really deal with very large polynomials in the post-quantum world, if you want to multiply them in the classical manner, then we have got an O(n) squared complexity, because the usual way we describe the polynomials are with their coefficients. On the other hand, there is an alternative way of expressing the polynomials also, which is based on their evaluations. So rather than, for example, choosing like 4 coefficients in a 4-degree polynomial, you will probably evaluate the polynomial at 4 points and just multiply them in a point-to-point manner. And this gives you an O(n) kind of implementation. So therefore, the real crux is in transforming your polynomial. And here is where entity plays a role. So we looked at the corresponding entity for Kyber and found out that the prime essentially is in a manner so that it's kind of different from the entity that you have for dilithium, and because the prime is different. So the question was, how do you really unify them? And we came up with a unified architecture where till a point we essentially kind of shared the dilithium and the Kyber computations, but finally we follow the dilithium computation because it has got a higher degree by an additional step, which is based on the famous Karatsuba multiplier. Now in Karatsuba, I mean, I'll just give you this quick idea that it usually tries to kind of optimize the multiplications by corresponding additions, because additions are believed to be more efficient than multiplications. So with this background, we came up with a combined entity multiplier. The idea is that it can perform multiple entity multiplications at the same time, and it can also perform the forward entity, the inverse entity, and also the point-to-point multiplication in a very, very configurable manner. So the entity multiplier also interacts with a block memory, which essentially has got the input coefficients which are being stored, and that essentially provides an input feed to the entity multiplication. The other important step that we needed to look into was the hash functions, and we looked into the KECHAK in this context because that was the primary block that we implemented, and essentially using the microcode based implementation, we can cater to various versions of SHA-3 and SHAKE, which are important hash functions which are used in these algorithms for various purposes, including pseudorandom generators. So finally, we came up with a parallel scheduling of the key generation of Kyber and dilithium. And you can see here, if you look into with care, you will be able to see that a lot of steps can be parallelized, but certain steps cannot be parallelized. And therefore, right, we came up with a, like an effective scheduling, which essentially can be performed with the reasonable hardware that we had afforded. So with all these things, we came up with a complete end-to-end implementations, and here are the kind of rough overview of the resources that are required on our platform. And in particular, in this particular target, which is an FPGA-based implementation, or a FPGA-based prototype, we can see here that the KECHAK and the entity multiplier forms the main components in the hardware design. And finally, this is the kind of comparison of our design with various counterparts. And as you can see here, that the area time product is really, really kind of, I would say, lucrative compared to the other designs. Area time product is important to measure because ideally you would like your hardware to have the least area and, to take the least time. But the area time roughly stays constant if you do not do innovations. And therefore, right, we believe that we have a fair amount of innovation to reduce the area time product of our design. So finally, after you are pretty satisfied with your hardware design, comes the, important goal of protecting against side channels. So in side channels, it really doesn't try to kind of break your hardness of the problem, but tries to kind of have another, side avenue to kind of know the secret key. But it is an extremely important vector because even NIST considers this as a part of their evaluation framework and tries to kind of evaluate the various side channel vulnerabilities. And that is one of the important criteria to choose one finalist over the other. Now, there can be various kinds of side channels. There can be passive adversaries, which basically tries to look at the power footprints. There can be active adversaries, which probably tries to actively inject faults in the computation and break your crypto systems. I will really not have time to talk about the passive adversary, but let me give a very quick overview about the active adversary and tell you how your crypto systems in the post-quantum world can be manipulated by very simple faults. So let us look at a potential KEM decapsulation algorithm and imagine that there is a fault that has been introduced, okay, which has been introduced here. Now, as you can see here, that there is this Fujisuki check which has been done, and this, one of the reasons you do this check, Fujisuki Okamoto check, which you do here, is basically to kind of enforce the CCA security. So the idea here is that if your fault is ineffective, then you will probably be here, and if the fault is effective, you will be in this area of your code. Now, the point is, the faults can be of two types, effective and ineffective. So let me try to give you a very quick overview in this context. So this is the decoding of Kyber. And as you can see here, that in this graph, there is this ciphertext space and the corresponding plain text. And this is how the kind of, if you properly choose your, inputs, then this is probably the distribution that it will look like. Now, the idea is that for this region, the decryption gives me 1, but for these regions, the decryption gives me 0. Now, suppose there is a fault and the fault skips an instruction. So this is the instruction which gets skipped, and because of which the distribution shift by around Q by 2. Okay, and Q is your parameter that you choose for your post-quantum implementation. Now, what happens because of this? You can see here, because of this shift, the green parts, as you can see here probably in the slide, you will see that they will be decrypted still to 1. If it was originally decrypted to 1, or if it was decrypted to 0, it still gets decrypted to 0, which means the fault is ineffective. On the other hand, for the red part, you can see that if it was decrypted to 1, now it gets decrypted to 0. And if here it was decrypted to 0, here it gets decrypted to 1. And this is an effective fault. So just by observing that whether the fault was effective or ineffective, you get to know the sign of the noise, okay? And as you know that in learning with errors, the error is extremely crucial, because if you have a notion about the sign of the noise, that means whether the noise is positive or negative, you can trivially you can form systems of equations which can crack the key, okay? And therefore the entire crypto system will collapse. So therefore it is important to protect against them, and there are a plethora of protections that people are coming up, but which also makes the cost higher. For example, you can shuffle the order of your computations, you can repeat the computations. These are all various strategies and countermeasures that you can try to kind of adopt. So finally, what is the future? Of course, we essentially are in a world where post-quantum crypto is extremely important, because we know that, there could be, adversaries which are harvesting now and will decrypt later. And therefore, it is an extremely important threat to our national security, and therefore we need to kind of come up with protections. And what is the ideal transition step? So yes, we'll have standardizations, and standardization will grow, but it is extremely important to improve our understanding about the post-quantum crypto algorithms and come up with proper understanding, so that we can also, not only understand the hardness, but also come up with suitable designs. Because until unless we have suitable designs which are protected against, side channel and other kind of lateral adversaries, we will not get an end-to-end design. So therefore, I would rather stop at this point, and if there are any questions, I would be very happy to address. You mean to say implementations? Yeah, so at this point in our designs, we have used entity-based decompositions. So for example, for Kyber, we have used certain splits of entity, and we have used all these, like Kulitaki and the normal algorithms, so that they essentially can be, not only realize the functions, but also make it efficient. So our objective was that we wanted to share the data path of dilithium and Kyber, and dilithium had a larger parameter. So we kind of, used as much as possible both the data paths to compute both dilithium and Kyber. But for the final steps, we had used a Karatsuba based decomposition.
Okay. Now, another question, what are the vulnerable areas where you need side channel protection here? Because I read somewhere, compress, decompress. But are there any other areas, or only those are sufficient?
So I would say that wherever your secret comes into play, and usually, right, we have this S, right, which is a part of this. So wherever the secret comes in your computations, you need to kind of what are called, do something which is called as masking. So you basically, choose a random number and you try to mask your actual data. And in this algorithms, often you will have various arithmetic components, you will have Boolean components. So you need to choose appropriate masking. Like some of them will be arithmetic masking, some of them will be Boolean masking, and often, these interoperating portions can be kind of tricky, like where you go from the arithmetic domain to the Boolean domain or vice versa. So we need to have suitable care over there.
There is a intriguing possibility, despite all the things you talked. I think we're well taken, very nice. This harvest now thing, why not prevent it by every year double the RSA modulus? 2048 to why double, quadruple? And I'll tell you why you can double it very easily, because anyway, all this entity, everything is in play. They might as well play for modular experimentation and RSAs. So my point is just this. I mean, of course, I don't know. You read new ones, new crypto, new stuff all the time. Anyway, 20 years old. But if you scale the RSA ECDLP parameters by 4 to 8 to 16, use entity everywhere, you will still be reasonably well off. But preclude this quantum machines for some decades.
Yeah, I mean, I probably get what you're saying. I mean, I would also like to mention that one of the reasons why probably we should look into these class of crypto systems, again, I think as what was also mentioned, that these problems do not have as much history as probably the RSA problem, for example. Okay, so they are lesser studied in that context. But many of these designs, like which we do usually are matrix vector kind of operations, right? Because we do in LWE and those things, we multiply matrices with vectors and so on. But they can be often made efficient to be even more efficient than their pre-quantum versions actually. So I think not only from the security point of view, but if you properly optimize, then there is a good chance that if these post-quantum algorithms can actually become more efficient than their pre-quantum versions.
There you are right. Yeah. Because these post-quantum algorithms are subquadratic, even almost linear in some cases.
Exactly.
Whereas that will remain cubic.
And you can really parallelize them. You can parallelize these implementations.
Probably, and then with all your IoT and all that.
Right.
Maybe. Okay. So it's good to change over.
Yeah. That's also true. It is good to be ready. Don't think there are any questions.
Any more questions? Thank you so much, sir. I would like to call Dr. Misbah, Scientist F, CDAC Bangalore, to felicitate sir with the memento.
We are almost at the end of our two-day session. We will have a valedictory event right now. All the dignitaries are already here. Professor C. Venimadhavan sir is there, and then Dr. Anand Mohan sir. All are there. Just stay tuned for some more time. We are just waiting for some announcement. मेरे पास है जाके बोल दो सर Meanwhile, we are very privileged to have Professor C.E. Venimadhavan, distinguished professor from IISc. Sir is known across the nation as the authority in cryptography. So we'll have a short talk from sir. I'll just briefly read the profile, obviously, which will not cover his entire life career achievements. So it is just an abstract of what sir has done. So Professor C. Venimadhavan obtained his academic degrees, BE Electrical Engineering from College of Engineering, Madras in 1969, ME Control Systems from BITS Pilani in 1971, and PhD Control Theory from Indian Institute of Science in 1975. He worked in the industry, Air India 1976 to 77, National Informatics Centers 77 to 82, before joining the Computer Science and Automation Department of IISc in 1983. He was a senior professor in the CSA department, Computer Science and Automation Department, and retired formally in August 2014. He was the chairman of CSA department during 1998 to 2000. He was invited to head the DRDO lab, SAG, New Delhi, during 2000 to 2003. So many youngsters are there. Yeah. Sir has asked me to cut short his profile, but I think there are many youngsters here who will see you as a source of inspiration. So let me completely read the profile, sir. So he was invited to head the DRDO laboratory, SAG, New Delhi during 2000 to 2003. His current research areas of interest are computational linguistics and pragmatic cryptanalysis. He continues to work in IISc on 3 R&D projects in the areas of cryptography and natural language processing. and on several technical advisory tasks spanning government policy and academic and research mentorship. He has worked on many scientific, industrial, consulting and development projects sponsored by government and corporate sectors in these areas. He has published over 80 papers in refereed journals and conferences and delivered over 200 invited talks in national conferences and universities. He has guided 16 PhDs, 12 MS, and over 100 ME theses. He is the co-author of a book on public key cryptography published in India in 2009. He is the co-author of a recently filed Indian patent on a new encryption algorithm. An international patent on this is being filed. Some of his project engagements were in the areas of cryptanalysis with Ministry of Communication IT, cryptology and cognitive networks with DST DRDO. He was a co-investigator in a multi-institutional consortium project funded by CEFI-PRA IFC-PAR during 2012 to 2015. The collaborative project between IASC, his group, TCS and University of Nice, France and Gemalto, France was on the design and development of various financial inclusion platforms on the mobile telephone infrastructure. He developed a system for handling e-cash and e-wallet applications based on a novel design of a digital analog of denominational flat currency. He also built a cash transaction simulator. If I remember correctly, that is called as virtual money, right, sir? So first of its kind in India, before this digital cash, digital money came into picture, sir had already introduced virtual money VM, that is called as, and also that VM relates to sir's name, Vinima Dhawan. He was the general chair of conference ADCOM 2017 of ACSS on the theme of blockchains and cryptocurrencies, and the chairman of the INAE Engineers Conclave 2017 on the theme digital economy. He obtained in 2001 an award by the Mathematical Association of India for distinguished services in mathematics education and research. He obtained in March 2011 an award by IASC for excellence in research and engineering. He and co-authors obtained a Best Paper Prize in July 2011 in Boston, USA in the annual conference of the Cognitive Science Society. He was an associate faculty of the Center of Neuroscience of IASC. He was the chief executive of the Society for Innovation and Development of IASC during 2006 to 2012. He is closely associated with the activities of the professional bodies, the Cryptology Research Society of India, CRSI, the Ramanujan Mathematical Society, RMS, ACS, INAE. He also works very closely with the government policy and R&D funding panels of the DST, IFC-PAR, MCIT, DRDO, NRB, NSCS, NTRO, and with academic councils of universities and research centers. Thank you very much, sir. I will welcome you for delivering the talk. Dr. Sir Anand, sir, can I please request you to welcome sir with the formal shawl? Yes, sir.
Thank you, Anand.
Registration.
He was my old friend and guru.
You know, he makes crypto. I try to break crypto. So that kind of friendship. Okay. See, I'll take about about 15 minutes. I thought I should miss the opportunity to tell something about future, and maybe and take it. That's okay. So I keep myself alive, looking at current trends and so on. So to make life interesting, this is just a short 7-slide thing. It's deep mathematical stuff, but without any mathematical symbol. All just verbs, phrases, terms, and so on. So much of which have been expounded so nicely in today's session and perhaps in yesterday's session, which I did not hear. The person, professor from Russia, then Devdeep and Anshuman, all academic researchers presented top-notch work going on in crypto in the post-quantum domain. So next 10 to 12 minutes, I'll just capture what will happen in the mathematical, algorithmic, and computational aspects of post-quantum world for the next 10 to 20 years, let's say. So we need to publish papers there. I'm hoping to get some done. Now, this is all a theoretical, algorithmic, as I say, mathematical, algorithmic and computational aspects of both design side and analysis side. Design is the crypto design, analysis is the crypto analysis. Okay, all I will call it pure academic bent of work. All the things about side channels and so on, I call side channel work. All very interesting things about what Devdeep presented. It's one thing to say about the fundamental aspects on which these things rest, but are we safe? So that answer lies both in the hands of theoreticians and practitioners. So I'll just tell you where we are in the theoretical world quickly. So, all these terms are the current last 2 decades and increasingly the next decade of research work which is going to be done. And so I try to capture them in a way you can take home in a nutshell. So fundamentally, mathematical objects and structures and types and function and operations on them will be done over lattices, codes, curves, equations, congruences, hash chains. These are the play of the next 3 rounds and the next coming rounds and so on. Okay, so you get a quick glimpse of what's going on in them. And as I promised, I don't want to put in, I couldn't put in this slides. Where I put in all the math stuff, it's about 80 pages, so it's not worth showing. Okay, now, so I capture in each one a design part, some fundamental principles, the converse, the cryptanalysis part, some fundamental principles. And obviously both go hand in hand. Crystals, PKIA NTU, number 3 research unit of Brown University, two moduli. So I'll tell a lot of words in the math stuff in words or like this. 2 numbers P and Q, one of them prime, other not necessary. And then there are some structures called modules or polynomial rings or finite fields. That's where we work on the crystals and the lattice-based stuff of Falcon and crystals. These are stuff from abstract algebra. Then there are stuff from linear algebra, which are vector spaces and lattices over generally discrete objects called finite field elements in these cases. Now, there are 2 things about crypto design. Sender and the receiver should have a quick way of resolving things. Encrypt, decrypt, sign, verify quickly. But the man in the middle must find the same thing hard. How do you do it? You transform, generally speaking, a general version of a hard problem into an easy version for the communicators. And then the adversary faces the hard version. And it's done by a little magic, which is by a trapdoor one-way function, trapdoors generally. Okay, so that is done by various ways of transforming a generic instance into an easy instance by means of a secret, which is the private key in the case of public key cryptography. Okay. So this operates in all the 6 mathematical structures which I showed, but of which finally the crystals won over on various counts, total counts of many things. But it's possible there are other finite fields and algebraic structures which could be invoked to build alternative to the current lattices based on modules over finite fields, rings over finite fields. And there are other structures which are a little more esoteric but could be used. And then there are other quantum invulnerable trapdoors, I call them. So the trapdoor cases in these cases will be the hard problems which are mentioned in the next cases. By using a trapdoor, the sender and the receiver make it easy for each other, whereas the man in the middle finds a generic problem without knowing the trapdoor. So how to find the trapdoor is by solving a hard problem, which generally cryptanalysis is faced with. And these have to do with shortest vector problems and lattices, a nice diagram, which the previous speaker showed, closest vector problem, small integer solutions, all those stuff. With when you tamper a regular problem with a small error, it becomes hard. So it's a very interesting thing. And it becomes hard in the general case, the approximate case, the average case, but not so hard sometimes. So it depends on the parameters. It sometimes depends on the random numbers chosen and so on and so forth. The general hard problem can become easy to attack. And that depends on many things, which depends on some kind of underlying mathematical analysis. So these are what are invoked in cryptanalysis. And presently for lattice problems, there are some things called enumeration algorithms, saving algorithms. These are common in the integer factorization domain also. And there's another thing about studying all this together. You can draw ideas from use in one domain to the other one. One type of underlying objects to another type of objects. So for instance, lattices, codes, and learning with errors problems all deal with some little noise pumped into a good instance. So that makes it hard. Okay. So these are done, the inverse way of doing it is to be doing a combinatorial enumeration or an algebraic saving and so on and so forth, and hybrid heuristics and so on. So these are the current day papers in all these methods. Then there are ways to look at classical ways of doing this, and a quantum which can exploit certain types of grabbing some underlying structures to use a short type or a Grover type of a search, which the first case is extremely efficient, the second case is not so efficient. But one can still invoke both of them. So I already said, lattice problems, learning with error problems, the decoding problems in the case of codes, sometimes some types of integer factoring, certain types of discrete log, all have a bundle of techniques which you can play with each other. So this is the generic thing about it. Rest of it I'll just be very quick and summarize that. I don't want to take too much time, but you will see the underlying undercurrents running across. Codes, these are going to be the mainstay, and this is what I'm also looking at very closely with some younger students and so on. And in particular, why so? Because they are sound alternatives. They just didn't make it. And one thing about math and algorithms is they were quite well known. All these stuff were known 30 years before. Even lattice-based thing. Schnorr lattice thing, which is used in integer factoring, was displayed by our Russian friend, C.P. Schnorr. Though idea is known, it is still not very effective, that particular attack on integer factoring for quantum, as an alternative to the Shor, which is difficult, which is good in quantum, but hard in quantum practice. So we are trying to actually find somewhat lighter on quantum practice alternative to Shor, which probably will not do as well as Shor quickly, but quite well. And these are kinds of things, trade-offs called generally time, memory, data trade-offs in classical, but there it should be qubit, coherence time, noise freeness, all those trade-offs. Okay. So in all these things, chords are going to play a very dominant role, because the chords are going to be used in classical type of crypto, but quantum invulnerable, as well as providing elements of theory for building noise correction in quantum, noisy intermediate quantum. It's called NISQ machines, which are available today. Noisy intermediate state quantum machines, for which also you need error correction. These error correction comes from almost classical, but partly quantum state manipulation stuff. So in some sense, all of you youngsters who are doing PhDs should immediately go and look up your coding theory very well, which I am trying to begin to do now, although we started off 25 years ago and left off. Many kinds of codes. There is a website called a Code Zoo, and Code Zoo has a huge variety of codes, okay, 20, 30 codes. 3, 4 have been tried, and all these have to be tried in the crypto world to make, and the essence is that encoding a stuff by padding is quite easy. You know, you need redundancy bits to correct errors, detect and correct errors. But given a general arbitrary vector element, to check what could have been the message which corresponds to this, what you received, is a game of looking at a big vector space, nearest points in something like a lattice space under some other constraints and so on. So it's called the decoding problem. In general, it's hard most of the times, and computer science hard this way. But there are easy to transform decoding problems which are used for encryption by Beckley's or Neodrator or some schemes, and all those names are displayed there. There are different metrics. Instead of having distance between 2 points in a vector space, rank metrics in a linear algebraic sense, different types of densities on the generator and the parity check matrices. All those QC, LDPC are all linear, low density parity check, medium density parity check. The bike was mentioned. It's a bit flipping algorithm for decoding, and a variety of other codes. Okay, classical nice codes like Reed-Muller, Reed-Solomon all can come into play. Each one has some caveat which makes it a little more difficult to be used in the crypto world. But this will all be massaged in the coming years, and each one has a good property, not so interesting property, and so on. And they can come from many other codes. Already the LDPC codes using Gabardine person named code was used in one RLCE, and then it was abandoned, the rest. Different metrics, different finite fields and algebraic structures and so on and so forth. And they can also lend themselves to what are called quantum error correcting codes, which have to be used in any coming generation of quantum machines by whichever quantum state technology which is being used. Okay, that's one side. The analysis is even more fun because any new type of heuristic you come up with, by the way, these are breaking by classical Turing machines of the decoding problem quickly by various heuristics. So approximations, average cases, information set decoding. There was one paper in the yesterday, I think, list decoding, which gives you some subset of elements and so on. So again, they can be played the classical machine and supercomputing. In fact, that's another thing which is going to be in the architectural world, where there will be a quantum and classical machine operating together for quite a few problems. The quantum problem solving is only one of the, I think, 3 upper layers of input preparation and 3 outer layers of output extraction. So in some sense, the classical machines are going to have a big role to play along with the quantum machines, even as a technology, but as an algorithmic means also. Finally, I just close up to say some what they call also RANs, but beautiful theories on elliptic curves, isogenies and elliptic curves, which didn't make it a very good structural idea as opposed to the elliptic curve discrete log based conventional cryptography. The elliptic curve isogeny based cryptography it was invoked. It's a beautiful idea where the hardness of the discrete log problem disappears somewhat, which makes it somewhat invulnerable, which made it invulnerable look to quantum, but again something else failed, so it lost out. But the isogeny computations are harder, but the newer ideas, but older machinery called expander graphs, and their spectral properties are coming into play. Some names like Ramanujan also are involved in the names of graphs of that kind. Okay. And there are generic methods of attack in classical, which can be invoked to attack them. It goes on. So 4, 5, and 6 have to do with other also RANs in the race, in the Olympic race for the post-quantum equations, congruences, and one oddball candidate, hash chains, okay, which is not in the same genre of mathematical objects. Equations and congruences have been of immense interest in mathematics for a long time. Multivariate polynomial, in fact, just quadratics, called Rainbow, got lost out. Learning with error congruences, again, one of them lost out, but learning with error problems remain. Okay. The analysis tells us that they are a bit hard, quite hard, but the instantiations of the methodologies which are submitted, they lost. So there are probably newer ways of doing it, which the analysis involved, more heavy methods like Grosvenor basis and SAT solvers and so on and so forth. But lastly, this hash change is a game which is completely different. Okay? Just based on simple ideas, but somehow they brought it to vogue signing capability with means of one-way hash functions like thing, which are called tweakable hash chains. And again, they can be attacked by some what are called pre-computations and post-computations. Pre-computations perform store. Runtime do some computations. These are called time memory data trade-off attacks. And it's possible to attack them on that. But then it's possible to design as well. Sphinx was the name of the candidate. So this is the way. Now, only thing you can say is that there is a lot of scope for doing PhDs. And as somebody pointed out, next competition for of NEST for newer thing, which they will not resurrect. They will simply re-invoke some of these things. In fact, the fourth round already has the 3 other code-based things in the running along with Sphinx. So all the best to fresh PhD registrants and so on. Thank you. Questions at the time? You can take.
Is there any question?
Okay. I'll take questions online. Mail. Okay.
Questions are not necessarily break for tea now. So you understand breaking for tea now.
That's okay.
You announced.
We'll break for tea and then assemble back just for the valedictory. That's all. So that will be our last function. Thank you. We'll have tea and please come back within 15 minutes.
बोलो मेरे पास 10 बार पड़े आप ले लो मैं तो ये बोलता हूँ मैडम मेरे पास 10 बार मेरे पास 10 बार कार्ड पड़े आप कौन सी बताओ मैं देता हूँ कभी तो ये बोलता हूँ मूड होता था कभी क्या बोलता हूँ कभी क्या बोलता हूँ मूड होता था लेके चलता हूँ ना कभी क्या बोलता हूँ मूड होता था और मैडम क्या करते हैं क्रेडिट कार्ड कैसे हुआ की बात करता हूँ
I will contact you. I understand your I'm also to one of my
Kind of discussing it. Come get some demo how many? It's a webinar. It's a webinar, but it's like limited. Okay. Okay. Interactive version. Nice. Listing of the product. Yeah, attachment codes. Product listing is there. Have you interested also there? But I'm interested. That's what I'm saying. Listing and sales. Yeah, I have to give some plan. That's why I told you just put there it on the so in it I have only place one. What you are had a project on program. So yeah. Licensing you are doing to your own company. We do business supply control. We will use that market. We will have them that understanding. Okay, I have to give some comment. I will just try to put something. What I will say. Simply something you could have found in the game. This is not a considered cost. It's actually accident. It is not. That's why that's continuous time. I put somewhere to come in your substance. In game it will be there.
Yeah, good evening. Can I request Shubham and team to request all the participants to come inside? We are starting the validity function now. I request all the members on different stalls to kindly assemble in the front rows. May I now request all the members to please assemble the front rows. We are starting the valedictory function of this 2-day PKI International Conference. Can you please come forward? I hope my voice is audible there, right? And I request any one of the CDAC members to just go and request the members from different stalls to come and occupy the front seats here. Akshay.
This is one.
Okay, all set. So thank you very much. We will start the valedictory function now. I request our dignitaries, Professor C. Veni Madhavan sir, and, Dr. Anand Mohan sir, Dr. S. D. Sudarshan sir, and Shri Ashish Banati sir, to please come on the dais. So welcome to all the dignitaries on the dais. Now I request Shri Ashish Banati sir, Deputy Controller of Technology, Controller of Certifying Authorities, to address the audience.
I would like to thank everybody for being so patient, so interactive during the event. This being the 5th such event series is happening. This is the 5th conference in the series, and I think we have been interacting in the last 3 in a row, and I have seen that lot of improvements, lot of new initiatives have taken place over the every year. Something new has happened, and we've seen people interacting amongst themselves, exchanging views, and that was the sole purpose for which we organize. Apart from this being academic and industry, both participation from both of them, both the sides. First thing, I would like to congratulate CDAC for this really good initiative. The hard work which our CDAC team here, by Dr. Bala, Ms. Baji, and Sudarshanji, they have really put in great effort, and the participants, the numbers have improved over the years. Perhaps we can have still bigger conference, more interactions. So I was just discussing with Sudarshanji, can we also increase the participation from academia? Perhaps if the papers what are presented here in some extended version or something can get published in a journal, sir. You may guide us further, so that participation from academia should increase. we find that from the university side and college side, they are insisting on papers published in journals with some Scopus index score. I'm not a academician or otherwise, but I really see that that perhaps could increase the participation from the academia. From industry side, we are really happy. All our ecosystem, CCA ecosystem was here. They were really new topics were discussed. They discussed about mobile PKI tokens, its indigenization. Then one topic close to my heart is the hardware route of attestation surveys, which one of our CAs presented here. And that could be a game changer perhaps in future. So it was a really interactive session, and I congratulate you all who have really done well, and I think this will help the nation moving forward in the right direction and lead to Atmanirbhar India. Thank you again. Thank you.
Thank you, sir, for all the guidance and support. Yeah, yes. Sir. So now I request Dr. P.V. Anandamohan, sir, the PPC chair, Technical Program Committee chair for the IEEE PKI 2024 event, to share his few words. Yeah, you can come.
So, good evening. I have been TPC chair for last year also, and co-chair is Dr. Balaji. So actually, we have invited papers from the general research and technical community for papers on this papers in related areas. That is not only public key cryptography, but other areas, like IoT, then blockchain and so on. But we were very disappointed to see that most of the papers, are related to some other areas. That means, there is nothing related to cryptography at all. So finally, we could gather some around 30 papers which have some relevance to cryptography, and they have been, all papers of course have been peer reviewed, because as per IEEE Explore, we are supposed to get 2 reviews for each paper, and reviewers have been asked to give detailed comments and all that. So finally we have selected some 11 papers for the presentation here, and we have selected one paper for best paper award. So that was on the authors are not present here because they were present online yesterday. That is on the comparative study of recent information set decoding attacks for QC LDPC code-based Macaulay crypto system. Actually, Professor Beniman was telling, it is one of the most important areas for post-quantum cryptography, that is code-based cryptography. And this, the authors have worked on something known as LEDA cryptography. So this paper was judged to be the best among all the contributions. And let us express the appreciation for the author. Then, what I would like to mention is, generally, people should not think whatever they are doing is not great. For example, even for patenting, what we should do, we should gamble, we should try. If somebody says that is good, it is good. So what I feel is more submission should be there in the related area. Many of you may be doing some innovation in implementations, maybe an efficient implementation. Speed may be efficient, area may be efficient, if it is hardware. Okay, so what I feel is you should work more in the most recent technologies and most recent algorithms and try to make some contributions. And I hope, next year we get very good contributions from our others, in this area. Okay, so that, in fact, we want to give more awards also more awards and more encouragement we want to give. Government of India is actually taking a lot of interest in developing this technology, public infrastructure, and we are very happy that we are not late now, because earlier what used to happen, technology used to develop and we used to be late entries. But today, we are in the entrance of the post-quantum cryptography introduction. So at this time, is an opportunity for us to learn new ideas, implement, and then make a mark in the world. Okay, so these are all the words I wanted to tell. Thank you. Others are Saurabh Biswas, and two more others are there. Names. Thank you.
So this is the one. Thank you. Thank you, sir. Now I have the pleasure of inviting Professor C. Venimadhavan, sir, the chief guest for this valedictory session. I request you to address the gathering, sir.
Thank you, Balaji, and thank you all, friends. And thank you as institutions, CCA in particular, the MAITI and CDAC were prime movers of this whole endeavor. And it's nice that it's the 5th year running in succession and in this nice place. I have a short comment to make on what Anand Mohan mentioned, and which we have been airing about it in many of our joint moving together here and there. This kind of conferences have a certain role to play, established, regular, so that the featuring in this you can highlight in your vitae. See, that's first something very important. And making a conference paper, presentation, everything ought to be taken seriously, but then it also should have the prestige it carries with. I think sometimes one is not very clear about it and all that. But despite all that, we should increase the our own contributions to our own indigenous intellectual initiatives, besides all other things. One short thought occurred to me just now. I just mentioned it. PKIA. People are going to ask you, what conference is this? You say it's public key infrastructure. Oh, it's CCA, it's government and only government and things like that. But one suggestion. Public key cryptography, PKC. PQC has a very prominent billing. PKC is very well known. Why not make it PKCIA? Just a thought. What happens is it's a cryptography name is there in between. So, and probably coding, everything is C. And people increasingly academic. By that, I did not mean anything special about academic. Research and development work, well done, ought to be published in refereed forum. And I must mention, Ananda, I have known him for a long time. He spent singularly a lot of time, many hours, whatever be the submission. So this conference requires many more good submissions. Probably it will come through with more dissemination of ideas. Maybe CDAC could do. CDAC is spread all over the country. So they should probably spread it across to all the institutes well in advance. Make an advanced calendar time. Give more time for refereeing. Tell people that it's a refereed conference. Because, over the last few years, which I've been fortunate to be involved with, it's gaining quite a good, I would call, attention. Very good material was presented. Even the contributed papers, a few numbers, though, were quite good. So I request that somehow we spread the message, either by a slight tinkering with the name and some publicity. Thank you. But otherwise, I thank CDAC, who are my good friends for a long, long time, for an excellent hosting. Thank you.
Thank you, sir. Thanks a lot for your encouraging words. Definitely, we will look into the directions and work on that. So now it's time for me to welcome Dr. S.D. Sudarshan, who is the Executive Chair of CDAC Bangalore, as well as the General Chair for the PKIA 2024 conference event.
So once again, namaskaram. Good evening to all of you. So, we have heard few things in a summary since yesterday morning from the best in the business as far as PK is concerned, giving specific suggestions. And definitely it is time. That's the reason I have been asked by Dr. Balaji to speak at the end. So that, because we are accountable in the end. Once we coordinate for all the credits and nice words, we get applause. But it's important to introspect and do better than what we are doing. It's not that we are doing bad, but what can we do better? So from that perspective, I'll start from the level of the conference itself. So I think Professor Anandamohan sir, as well as Professor Venimadhavan, and yesterday Professor Shyam Sundar, everyone has pointed out two aspects. One is this area deserves a unique place in terms of research conferences that we need to do. So in terms of theme, in terms of importance, in terms of business volume, given that digital trust and digital economy is growing, it's a very important area. But the second aspect is how to reach out to larger, both geographical as well as domains who are involved in the area of PKI at a higher level, maybe technically the public key cryptography, PQC, and all associated aspects. So here, sir, yesterday we have had a discussion. So the journey started as an event by CDAC, supported by CCA. That is how we started. Banati sir has been part of it since inception on this. So he knows the history. So first 2 years it was done like that. Third year we had IEEE officially making it an IEEE event. So today we have IEEE Computer Society as well as Industrial Application Society. It is officially the conference by them. Normally IEEE people get a technical sponsorship by paying, and then we follow certain protocol. Here it is an IEEE conference. So that way we are into the core. So after the first 2 years, the quality was recognized and we are going. But yesterday, 2 events with them. This is the third time we are doing with them. Now they have said, and of course, Dr. Prasant Mishra, you all know, he was with Computer Society, now he is with IAS as chair. And I was IAS chair in addition to being CDAC KD last year. So now we are going to reach out, try to change this to a IEEE global event, not a society level at the Bangalore level. It is going to scale up, which means the IEEE e-notice will reach out to the global audience by default. Today we specifically request them with a e-notice, and we have to do some formalities to send the information to the larger audience. So that is one part. Parallelly, we are in discussion with R10 Council of IEEE, so that at least the entire Asian countries and others will get covered, for whom Bangalore is a dream destination. So these are the two initiatives are happening to reach at a global audience at a larger level. So for the next year, we will be planning the conference with the tracks that can be domain specific, quantum, AI with PKI. That kind of things have been discussed. So we hope the next year event will be an officially global IEEE event. So that is one thing. The second aspect is we will be announcing probably not the best paper award just like that, along with some prizes. I think any incentive is always taken in a positive spirit, and it is good to put on the resume. I received this award, not just the best award, because if it is just a certificate, it can be done in many ways. But the moment there is something in kind or cash, it is showing that there is a real commitment by the organizers to choose, because money cannot be spent just like that. So that is the second aspect we are trying to do. And third thing, that is what Bhanati sir was indicating. We have been doing it very, very informally so far because of the total number of accepted papers that are not very huge. But going forward, we will make it a practice that each accepted paper, because we are accepting hardly 10% of the submissions, which is at par with the globally A-star rated conferences in terms of acceptance rate. Being the case, the extended version can also actually be converted into a journal paper. So today we have both a number of IEEE transactions. In addition to that, we have access to Sadhana journal, which is our own. In addition to that, we also have a good access to the ACM team. As we speak, Bangalore has some connection with all the top. Today, ACM India is headed by Professor Meenakshi D'Souza, and IEEE R10 is headed by Professor Das, and the Sadhana journal, Professor Shyam Sundar is the chief editor. So we have all the right connections, decision making level. Technically, we have stalwarts on stage right now also. So that's not an issue. So we are going to ensure when we publish here, they also get a follow-up, either a journal paper or a book chapter, which will enhance the value and incentive to participate. And now that the calendar is more or less frozen, typically the first Friday, Saturday of September, that is what we have been doing. But for Ganesha, it would have been today and tomorrow. That is how it would have been. So we know the dates upfront. So we'll announce it early. Normally we have taken a little bit time to announce, and we have given time till April or so with extensions and all to submit papers. We'll have to push it a little earlier so that people can plan their travel funds to be physically present here when it is international. So that is something we are working on it, sir. We will do it. That is a commitment from our side, both the Office of CCA, Professor Venumadhan, Dr. Ananda Mohan, Professor Shyam Sundar, and the IEEE team, which has been supporting. The second aspect is that the feedback about the keynote speakers and the invited talks this year also has been extremely positive. And in fact, people have said that it is worth attending only for the keynote itself by paying. Today we have so many webinars, so many YouTube channels. In spite of that, such a comment is very heartening. And the hard work and the dedication shown by our team, our TPC chair Ananda Mohan sir, along with the, and not just Dr. Balaji, along with him we have Dr. Misbah, Anup Pandey, Gopinath, a plethora of team. I have to say that because today there are more than 20 people at the backstage who have been working on this from CDAC alone, in addition to the committee members. And we have also the privilege of informally requesting Arvind Kumar sir and Bhanati sir to reach out to people if we need to use that channel, and it has been very effective. Next year we would like to have not just the level of the conference higher, But the exhibitors or exhibitions that we are looking at it, we will also have some very specific brainstorming sessions so that the research reaches industry and vice versa. That is what Anandamans were talking about. You can present your innovation at various levels. So you can do the science part of it, you can do the engineering part of it, you can do the domain part of it, even you can do the packaging part of it. How did you package it to make it a useful solution? Because today we have too many solutions funded by various agencies. How many of are usable? It's a big question mark because we fund scientists, but we don't package it and deliver. It's a global issue, not just in India. So there is something that we need to work on. We'll enable in this conference. That is something we'll work on. And the support we always get from the industry ecosystem of certifying authorities, sub-CAs, the token manufacturers, trainers, it has always been amazing. It is to that extent that we had to turn down a couple of people who wanted to put up a stall because of the paucity of space. That is the kind of response that we have been having. Yesterday evening, many of you might have seen the interactions that were going. It was almost like an industry conclave, not like a research conclave. Because there was a product launched, visitors coming, sitting in the round table, discussing where to take to the next step. How couple of the people can collaborate to give a larger value to the end customer, improving the business overall. So this has been an amazing experience for us. And lastly, we will see if there can be a separate tutorial come demo section that can be added. Either one day before the conference, the way we have pre-conference tutorials and all. Because reaching out to the larger audience is extremely important. It is one way to do that. That will also enable various academic institutes to come in bulk to attend, at least for the tutorials and the demos where they can see things happening. Those are, ideas that are currently under evaluation and we'll work on it. I cannot say enough to thank each of you for being here. The authors, the speakers, the TPC team which reviewed, and of course the entire TPC team effort is probably maybe a bit less than the singular effort of Dr. Ananda Mohan as highlighted by Professor Veni Madhavan. So that is something that has added a lot of value. And the team has done a very, very good work, both from CCA side, IEEE side, and CDAC side. Whether it is administration, registration, everything has gone smooth. And just on the positive note, both since yesterday morning to till now, we have exceeded the estimate by at least 30% in terms of audience present here. So that was the reason we have that many extra chairs put. And that is really amazing given that yesterday was Teachers' Day, today is Gauri Ganesha and tomorrow is Ganesha and people are in a different mode. So that shows that there is value to the event and the percentage of invite to acceptance to physical presence, that ratio indicates the value attached to the event. The fact that we got almost 25 to 30% higher on all the counts on the average, that is what is satisfying to us and very gratifying. So thank you one and all. I compliment each of you for being part of the journey and thank personally on behalf of CDAC, on behalf of CCA, on behalf of the as general chair of the conference for the entire team and IEEE. and from Engaluru, Bangalore. So with that, I'll pause here. Thank you, sir, for your time spending the whole day. And we learnt a lot. Good experience. Now, Dr. Balaji.
Thank you, sir, for not only setting higher level of goals for the next event, but also forging or highlighting what are the four possible potential collaborations that can be made at the national level and the global level to take the event to the next higher stage. So thank you very much, sir, for this. So now as we move on, I request my colleague, Dr. Mohammad Misbauddin, as an organizing chair of this particular event, to announce the felicitations and propose the vote of thanks. Welcome.
Thank you very much. Thank you, Dr. Balaji, and all the dignitaries on the dais. This conference had generated more, name as well as, the awareness, because what we have seen in the last 2 days is not only it has covered the basic aspects of digital signatures, but it's also covered post-quantum cryptography, and then from the process point of view, security process and procedures for aviation industry. So different types of talks were there. And in addition, we also had the demonstrations directly by the exhibitors here who are, who have their own solutions, including indigenous solutions. So as a token of appreciation, I request the dignitaries on the dais to kindly felicitate the exhibitors as well as the sponsors of this conference. We had 3 gold sponsors here. So I'll announce one by one. It is not in order of merit, but just whatever we have written. So may I now request any representative from Thales here? Yeah, can you please come on the dais? I also request now Odyssey Technologies, madam. Representative from eMudra. We have now the felicitation for the silver sponsors and other sponsors. Zoho Sign, representative of Zoho Sign, can you please come on the dais, madam? Next will be Sinex. Representative from Sinex is there. Anyone from Sinex? Okay, moving on. vSign, Verisys. ID Sign. Any representative from ID Sign? Yeah. Next is PentaSign. Any representative from PentaSign here? Okay. Prodigy Sign. Precision. Members from Precision. They were here, right? I think, can someone just check Precision and other people? Yeah, Care for Sign. representative from Care for Sign? Okay. We had another stall from CDAC Noida. You are from CDAC. Surprise. Capricorn is there? Already we have given them Capricorn, they have left. Okay, thank you very much, sir. So just I would like to propose the vote of thanks. First of all, thank you CCA sir and Office of CCA, Deputy CCA Shri Ashish Banati sir and all the members here. Every time whenever we are conducting this conference, they are making sure that they are with us. That is why this conference is becoming a success as well as a series of successful events now. And Executive Director Dr. S.D. Sudarshan for supporting us as well as guiding us at every step in smoothly conducting this particular conference. And of course, I should not forget the ED office. Ms. Srikala is not here right now. So continuous, we have continuous support. In fact, I should not be wrong. I'll not be wrong if I am saying that she is giving us 24/7 support. So thanks for her in her absence here. And Arnab is not here. Okay, so thanks to him. Apart from that, the reviewers, there are many reviewers who are anonymous. Okay, they have just done the review, who might not be present in the conference also. Without them, the reviews would not be possible. And obviously, the TPC chair, sir is here, Dr. Anand Mohan sir is there, and co-chair, Dr. Balaji, and Professor C. Madhavan sir, and speakers. There are many speakers who have come from across India, as well as from US, there were 2 speakers who have joined remotely. And from Russia, we had 2 speakers who had joined remotely. So I personally thank to them as well. And authors of all the papers who have attempted, many of them, many papers have come, but whoever has presented here, my special thanks to them as well as those who have also submitted, and they always have the chance for the next PKIA conference as well. And organizing team, a big thanks to all these youngsters who are standing here, and they are here for last 2 days continuously. Mr. Anup Kumar Pandey, my special thanks to him, silently doing everything in the background. So big round of applause for him as well. The entire PKI team, led by the RISE team, led by Dr. Balaji. So the PKI as well as DNS, all those teams are under him. Mr. Gopinath is here. Jitendra is somewhere. Jitendra Kumar is there. Dr. Sanjay Adiwal. So they are making it possible that every event is a great success. My special thanks to admin headed by Muthu sir is here. He was here just now. So Mr. Muthu Kumar, yes, give big round of applause to him as well. Supported by Mr. Arun Shankar as well as Mr. Sali and all the members. So they were continuously on the run for last 2 days. On the run should not be taken as negative. So MMG in the background, they have made it possible. Whatever we are seeing here, MMG and finance and all the exhibitors and sponsors. Thank you very much. Thank you again. See you at PKIA 2025.
So before the group picture, I request Dr. S.D. Sudarshan sir to felicitate Professor C. Madhavan sir, the chief guest of the event. Sir, you can be seated. Yeah. So I request all the members to join for a group photograph here. So I think, yeah. CDAC team, CCA team. Yeah, please. Yeah, all the exhibitors and all the participants. Yeah.
You also have us.
No, he said no. I told him that he can't. No, no, we'll do separately. That's what I told him.
सामने कौन कर रहा है
We'll sit now here.
Yeah.
Participants, can you come? All the participants. Whoever wants to have a picture, please come.
All the photos, videos, presentations, or even the stream, whatever talk has been given, everything will be uploaded on our website and it will be available at pkindia.in/PKIA. In fact, you can also view last year's videos and presentations also. Thank you.